in, then maybe just put up a thumbs up emoji, and then we will just call you. All right.
I have a feeling, Jim, most jurors will have similar, if not same questions. So I don't think there'll be problem of time. I think most of the time goes in them answering as opposed to jurors asking.
Yeah, for sure.
So I like the idea of typing it. Most people will just see the typed question and be like, same.
Yeah, I don't think you clicked my name on the juror list. Whoever's doing the screen sharing.
Oh, this one?
No, SHANTANU. I put my message. I think mine was at the very top in the chat, so you might have missed it, maybe.
SHAN.
Oh, you did get it. Sorry, that's my
yeah.
bad. Thank you.
Yeah, I got everyone starting from the top.
Are the three teams here? I see Shroomskis, I see Schwarzschulen, I see MMM. Okay, so we should have two teams here. Just hold on for a second before we submit, and then we'll submit right at 3:45. Okay.
Also, the live stream is live now.
Okay, cool.
The same.
Did we change the thumbnail?
I'll change it a bit.
Okay, we're not OYPT. Right? Let me be the first person to like. Oh, I should put up the my background. So Dave, you're gonna do the live chat. You're gonna talk to our friend.
On the live stream?
Okay. Yeah.
Yeah, sure.
Will you have friends from SG joining?
I think it's quite late at night there, right?
Quite late at night, okay.
Maybe the ones that are in the US.
Let me send you the awards stuff. Oh, yeah, so for all the jurors that are here, maybe you could use this time before we start to quickly think about whether you want to nominate anyone for our individual awards. So we have two individual awards. We have Best Theory and Best Experiment. So you can just think back to the 5 selective rounds and then think who do you think deserves this award. And you can let us know your nomination in the juror Discord channel, right? Andrew, how many jurors do we have in the system right now? Check.
Yeah, 1, 2. 19.
19, okay.
Are you charging or?
I'm not.
Okay. Yeah, so we have 19.
Okay, that's fine. You sure the system can accommodate that, right?
Yeah.
Okay.
There's
Wonderful.
no upper bound.
Let's not test that.
I mean, it has been tested before.
Andrew, I remember the first year we were doing this. We were still in person. And then you had to leave, and then I messed something up. I think.
Well, this is the what, 3rd? Yeah. 4th year.
Yeah. Which year was that? Like 2020? It was, right?
Yeah, I guess 2020.
Yeah, it was like like literally 2 weeks before COVID hits. So
Yeah, that was like way back when
yeah,
I
it's way
was
back.
when I was still a ninth grader.
And hopefully next year we will hopefully go back to in person.
Jim, will you be posting the live stream link somewhere?
Oh yeah, so you can just go to our YouTube channel, or maybe Dave, you can post the link in chat.
Yep.
Must admit, we've never had this many jurors
Thanks for the link.
in for the finals.
No worries.
Thanks for that, Jim.
Cool. This thumbnail is it's really
Oh, the YouTube thumbnail?
yeah.
Yeah, I'm getting spammed about the YouTube thumbnail.
That's,
I will change it in a few minutes.
the question is, will it update in time before
Doesn't
we
it update like
finish?
instantly?
Does it? I don't know.
Okay, that's okay.
Yeah, we'll start at 3:45.
Can someone just check the stream audio really quick? I don't know if it's working.
I can check.
It's working. I just picked it.
Thank you so much, Ethan.
Is the audio fine?
Yeah, Jim. Audio seems fine on YouTube.
All right, cool. Wonderful. All right, so for the individual awards, so I'm getting a question from Reza. So individual awards, so essentially you can just think back to all the presentations that you've seen in the selective matches, so like round 1 to round 5, right? You can think which presentation had the best theory, which presentation had the best experiment in your opinion. that is worthy of an award, and then you could let us know in the juror channel, where you can like DM me. That's also fine. So just let me know who you nominate, and then we'll take that into consideration. We'll take everyone's nomination into consideration. We'll take a look at the marks that they got, and then we will announce the winner during our award ceremony.
Jim, do you have the template for the thumbnail you made?
Pardon?
Do you have the template for the thumbnail that you made for OYPT?
One minute. Let's hopefully. OYPT one, right? Or actually.
All right, that's fine. That's fine. I think you should.
Okay, so sure. Let's get started. So last call for any jurors that wants to join. That's not checked here. Just speak up if you're not on the list that you want to judge. Right. We reached the end of our list. So that's good. So are the three teams here? Could you guys speak up to make sure that you guys are here?
MMM. MMM is
Okay.
here.
MMM is here, and just to confirm, you guys are presenting the magnetic mechanical oscillator, correct?
Yep.
All right. Is Team Schwartz children here? Team Schwartz children? Speak up.
You're here.
Okay. So just to confirm, you guys are presenting Ponyo's heat tube, correct?
Yes.
All right, cool. And then Team UTS Shroom Skis, you guys are presenting colored line, correct? Shroom Skis?
Yeah,
Yes.
we're reporting colored line.
All right, cool. So, okay, I guess we can get the final started.
Okay, so
Submit.
submit that. And now 3 teams, all the jurors, going to activate it. And release. And finally, we'll publish it. Okay, so we can get started now with the final match. So do I draw just in the order of ranking,
Yes,
right?
so if they do that, then who's presenting first?
Schwartz children.
Schwartz children. Okay, so then we should do it the other way around.
Okay.
And then Schwartz children, they're doing Ponyo's heat tube, which is problem, let me check, which is problem I, yes.
All right, okay.
Okay. MMM, they're doing magnetic mechanical oscillator, that's problem E.
E.
And then Shroomskis, they are doing colored line, which is problem D.
Okay.
Okay. All right. Cool. Oh, you need to check the drawers, eh?
Oh yeah. So many. Okay. So let's submit this. Okay, so stage 1.
So who will be reporting on behalf of Shroomski? So I would like to remind everyone that in the finals, each person in a team can only go on stage once. So that means your reporter, your opponent, and your reviewer within your team has to be 3 different people. All right. So Shroomskis, who will be on stage?
Crystal Lee.
Crystal Lee. And for MMM, who will be on stage?
Archie.
Archie. And for Charles Children, who will be reviewing?
Sorry, Jim. We just want to make sure that right now it says reporter is Shroomskis, but the problem is Shore's Children's problem.
Oh, this is Schwarz Children's problem. All right, we can just let that be for now. We just let that be for now. And Andrew, is there some way to change that still?
No, but
Problem
we
name?
can do it later.
Yeah, we can change that later. And it wouldn't show up in the ranking anymore.
No, it doesn't.
Anyway, so we'll just keep track of that ourselves. So Schwarz Children, who will be the reviewer?
Just to make sure
for you.
the real problem that's reporting is colored line from Shroomskis,
Color
right?
lines, right?
Oh,
from
okay.
Shroomskis.
The reviewer will be Arya.
So that's correct. Everyone's good with it. Andrew, please submit. All right. So let's start with a preparation of the reporter. 5 minutes. So for our stage 2 and stage 3, we will not have a break time in between. So if the jurors wants to take a break, we can use the 5 minutes of preparation of the reporter to take a short 5 minutes break. All right. So when Jura asked the question, for the Jura question, you could just say it out loud, and I will point to whoever have their little hand emoji up, and then you can speak up. All right, reporter, please have your slides ready on screen. We will start shortly. All right, Andrew, please advance to the next stage. Rumsky, are your slides ready?
How do you share?
Okay. You have to press the
Oh, all right, Andrew, you can start the timer.
Oh, okay. And then power. Hi everyone, my name is Crystal Lee and I'm from UTS Team Streamskis, and I'll be presenting problem D, color line. And I do want to preface this by saying that this was not our original final problem, but we are dedicating this problem specifically to honor Archie Shu, whose birthday was yesterday. So everyone in chat send him a quick happy birthday. Now, moving on to the actual problem itself, and that aside, the parameters we'll be investigating today are the position of the observer relative to the light source on the horizontal plane, and also we're going to be varying the angle of the disk as it relates to what angle the light hits the disk at. And this is a quick overview, and most of the quick overview of my presentation today, and most of it is going to be qualitative analysis, and I'll explain why later. And this is just a preliminary observations about the phenomenon, and as you can see here, and as you're probably all familiar with, if you shine a light on the CD disk, a rainbow line appears. And then if you can tell by the proxy marker, what this proves is that basically the angle of the, or the position of the observer relative to the stationary light source does affect on which, where the line appears. And this is the experimental setup for this problem. So for this problem, the light source that I used was a 4 watts LED, and then also used CD and also the markers. So this is the setup. The observer is an iPhone camera, and then the disk was set up on the same horizontal plane, which is 60 centimeters above the ground, and the light. And on the left, you can just see the setup in broad daylight, while in the on the right is just the setup in dark, aka when I actually took or did some visual experimentations. This is a picture taken from a point of view of the camera, and the point of the washable marker was that because the position of the line does change with an observer, what the marker was, is the purpose of the marker is to mark the position of the line at this specific point, so that when I take the disk off, I can do some measurements with angles and lengths, not lengths, but in etc. This is just a birthday view of the thing. And moving on to qualitative explanation, one thing to note is the disk characteristics of a disk. On the left, we have a CD, and what makes a CD able to record data is that there are little pits in between that are indented into the disk, and the spacing between each of these disks is 1.6 micrometers. And these pits are special in that they're all facing parallel to the center of the disk, so they're all in a circular pattern. And while the indents of these disks are called pits, the raised part of these indents are called lands. And this is terminology we'll be using consistently. And now I'll be going some major assumptions that will be required for today's analysis. And the first one is that refraction is minimal. Refraction is the bending of the light as it passes through an object with a different optical density than the current medium. And for the purposes of today, we're going to assume that that's minimal, especially as it passes through the protective plastic layer, polycarbonate layer of the disk. And because this layer is only a few micrometers, so we're going to, and it's also plastic, I believe that this assumption is valid. Another assumption that I'll explain a bit more on is that reflection in the pits can be ignored due to the large angle of incidence. And finally, that the light reflecting off of other objects is negligible. And Yeah. So as for why the reflection in the pits, I believe, is negligible, it's because of this problem statement only discusses light as it hits the ray at a large angle of incidence. Large angles of incidence are measured from the normal. So what this means is that as the incident ray hits the pit, it barely graces off it. And what it means is that according to the law of reflection, it will have to reflect back in this manner, and then in such a way that the light that comes out of it is difficult to predict and also unlikely to follow the same reflection pattern as the light that reflects off of the land or the raised part of the disk. Additionally, another thing to consider, and something that won't make sense until I explain more theory, is that as this light that grazes off the corner of the land, this introduces more chaotic rays into the system, and this is makes everything so much more difficult to observe. Okay, so let's begin with the preliminary observations on what happens to the incident ray as it hits off of these lands. And once again, we'll ignore the influence of the pits on these diagrams. One thing to note is that light exhibits constructive and destructive interference. So what this means is that the maxima of these wavelengths will constructively interfere to amplify the amplitude of the original wavelength. And knowing that, we can also draw wavefronts at where these maxima are going to be. And these wavefronts are drawn up in the direction of where the light ray is going. Another thing to note is Huygens' Fresnel principle, which says that each point of the wavefront is itself the source of multiple mini wavelengths, and the sum of these new wavelengths make up the new wavefront. So that's just it in action. And one thing I want to note is that these red points is on where the wavefront actually hits the disk. That's where we're going to be focusing on, and because these red points are also points on the wavelength itself, we can model all of these as new wavelets. So what this allows us to do is that by focusing only on the reflected wavelengths that we need to know, and using the well-known principle of Huygens, we can also draw the reflected, projected light rays and also the new wavefronts by just do geometric analysis, and that's what reflected ray. But another thing to note is that this ray can also be reflected in the other direction. And as you can see here, it's not the only direction that the maxima can constructively interfere. Ergo, we can draw a similar ray going in the other direction. And knowing this geometric model, we can also then model it as a special kind of reaction grading, which is reflection or blazed grading. And this is also experimentally proven when I've shown a laser directly on a disk to model the diffraction grading pattern that comes off of it. And as you can see here, like there is a light that's going to be reflected to the opposite side of the normal as the light source, but also light that's going to be reflected back in the same direction the normal, on the same side of the normal as the light source, pardon me. And what this means for separation of white light is that because this visible spectrum spans so many different wavelengths, we can then also predict that red light is going to bend more than blue light, just because of the points of these maxima happen to constructively and destructively interfere. And this is just some experimental verification on stuff outside the scope of the problem because of the small angle of incidence. But this is just further verification of the fact that we can model it the disk as a diffractive grading. Knowing all that, we can finally draw this combined cross-sectional diagram. So the maxima that's going to be reflected on the same side of the light ray, I'm going to label in the negatives as m equals -1, whereas on the light waves that is going to be reflected on the opposite side of the normal as the incident ray, I will label as positive. And knowing that, we can finally move on to theoretical models. So first, I'll be going over why do we see a line. This is switching frames of reference to look at the CD from above, so that the light source observer and disk on the same plane. We can then draw light rays coming off the light source to hit the disk. And according to the law of reflection, according to the law of reflection, what that means is that this light ray will have to reflect off the disk in such a way that the line bisects the space between the light source and the observer, and which is why we see a line. And as you can see, and this is the negative maxima that we can see on the left side of left diagram. And whereas on the positive maxima, that gets reflected in a place that doesn't return to the observer in the way that we can, in such a way that we can see a line. Ergo, that means that the angle between the line and observer must be half of the angle between the light source and the observer. And this is just experimental verification. And one interesting to note here is that the errors could be caused by random human error, by like misdrawing of the marker, or also systematic error, where perhaps one of the assumptions, such as that refraction is negligible, wasn't quite as applicable here in this situation. Second model, what happens when the angle of reflection is negligible, and why does it matter to why the line is green? So this is basic principles. We can once again return to the geometric model of a problem. So why, okay, so once a light ray reflects off the disk, so that these green rays are the reflected rays, and the again, spacing between the disk is 1.6 micrometer, or in this case 1600 nanometers. We can also see that in order for constructive interference to occur, that the spacing between each light ray must be n to the power of a wavelength. So using that, we can just use basic trig principles to come up with this. And knowing that, we can then calculate for different n numbers to get green wavelength with 533 nanometers. And for my final model, I'll be tilting the disk towards the observer, where the reflection angle is significant. Once again, returning to reflection grading equation, what that allows, modeling the disk as that allows us to do, is that we can use the actual reflection grading equation. So by assuming that the angle of incidence and reflection are extremely large, as is the problem statement, we can plug in the pitch spacing to get this theoretical graph. And the black box is just where the visible wavelength occurs, and this is just all the colors that could appear or you see on the disk, which as you can see on this is just there because most of it is around the 500 to 400 wavelengths down here. So that's why most of the colors you can see are pink and green. So for my conclusion, basically all I've went through the principle of Huygens as it applies to reflection off disk, and why we can do model as a diffraction. Also, I had a controlled experiment setup, and yeah, basically, thank you for your time.
All right, thank you for the reporter for your wonderful presentation. Could we go to the next stage, Andrew, with the opponent's question?
Okay, may I start on my questions?
Please go ahead.
Okay, so I had a quick question. I noticed that you only used an LED light bulb. Is that true? Did you use a filament light bulb? Because obviously LED only has RGB values, and that may affect your experiment.
Yeah, we only used an LED light bulb, but should it matter that much? Yeah.
I feel like it would, because obviously a filament lamp, which was introduced in the problem statement, does say that if a filament lamp has a larger wavelength and shows all of the wavelength of visible light. And I was just wondering, how did you figure out like the angle that your sort of lamp was sort of like going towards the disk?
For that, I had a camera that was facing horizontal. So as you can see, like I had a camera that was physically inside the setup, and also had a secondary camera that I just placed also 60 centimeters off the ground, and that was when I took like cross-sectional views, and that's where
and that's how you figure out the angle of incidence?
Yeah.
Okay. So did you experimentally determine the diffraction grading?
I experimentally verified it using just a laser reflecting off the disk.
Okay. All right. So you talked about how refraction doesn't matter, right? Why do you think that refraction doesn't matter in this sort of problem? The refraction index of a polycarbonate layer is, I believe, only 1.4. And because also since the layer is thin enough. Yeah, but water is 1.3 and the index of refraction, which means that the polycarb is greater, which I feel like would definitely affect the experiment a little bit, no?
Sure, we can discuss that later on.
Okay, sure. Let's discuss it later. How did you determine the CD grading? like the
What do you-
yeah, the CD grading. On slide 14, you said 1.6, I believe, micrometers.
That's known manufactured
No,
information.
okay, meaning okay. Last question is, you talked about how reflection. Do you think reflection is a big part of this problem?
Yeah, that's how you see the line.
For an answer.
Okay.
All right, cool. All right, thanks to both the reporter and the opponents. Andrew, next stage, preparation of the opponent, 3 minutes. Let's start it now. All right, opponent, let's try to get our slides up.
Sorry, can you guys see my slides?
Yep.
Okay, perfect. Hi, my name is Archie Shu from University of Toronto Schools, and today I'll be opposing problem number D, colored lines. And you can see the phenomenon happening here, where at different angles, you can see a very visible green line appear on a CD disc. The problem statement goes as follows. When a compact disc or DVD is illuminated with light coming from a filament lamp in such a way that only rays with large angles of incidence are selected, a clear green line can be observed. The color varies upon slightly changing the angle of the disc. Explain and investigate this phenomenon. And some tasks that we propose today to have a successful report is to first create a reliable, accurate, and reproducible experimental setup. Qualitatively explain the phenomenon. Investigating key parameters such as the angle of incidence, angle of observation, grading of the disk, predict colored line patterns using theoretical models, demonstrate that predictions sufficiently match observed colored lines, and lastly, analyze the impact of each identified key parameter on colored line patterns. So a quick summary of the report, she had an excellent qualitative explanation and qualitative theory to experiment comparison, and talked a lot about reflection grading on the experiment. Some merits and next steps, we thought that it had a really nice geometric analysis and sufficient qualitative explanation of phenomenon. But some possible next steps include varying key parameters and investigating relationships, such as controlling the light beam, improving their experimental setup, such as using filament light, turning off the lights when you're doing this experiment, or creating a stable measurement method, modeling the intensity, such as like the wavelength of which you sort of perceive, and theoretical to experimental comparison for each theoretical model, and lastly, predicting at which angles a colored line is seen. So an overview of the discussion I would like to propose today is firstly, how exactly you can improve this experimental setup to more accurately cover sort of the experiment and have have more, I guess, data points. And the second is that theoretical equations to really predict the green line in the first place. And third, some experimental verifications. And lastly, what are some possible key parameters that may affect the experiment as a whole? I would like to forfeit the rest of my time to the discussion period. Would you mind sharing your screen?
To a particular slide or?
Yeah, the slides. I wanted to just go to your experimental setup for a second. So any one of these slides would work, probably slide 7 actually. I just wanted to ask, when you were doing this experiment, did you have lights on in your room or was it just the lamp?
Just the lamp.
Just the lamp, okay. And how did you sort of like control the angle of incidence? I noticed that you're kind of putting a stand and a CD on an object and then the light on an object as well.
Oh, for angle of incidence, why I decided to tilt this disc specifically was because I put it on a tripod of a camera, and so what that just let me to do was just easily change what angle the CD was facing, so that I didn't have to do any funny maneuvers with the light or the observer.
But the issue that I'm seeing with this is, if you go back to slide 7, the light source has many different sort of light emitting diodes, and you sort of have a lot of light beams. I feel like that could affect the experiment a little, especially since having only one light ray hit the CD would produce a different effect, right?
Only having one light.
Yeah. So something, one light ray, or at least decreasing the light ray. So something you could potentially do is creating a slit for a cover of the lamp. So less of the light is actually sort of leaving the lamp, and close to one light ray is only hitting the lamp, is hitting the CD.
All that would change is the intensity of the light that comes out of the lamp. It doesn't actually change like the wavelength or number of rays that come out of it. All that changes is the intensity. That won't affect it.
Okay, but then you would get more random points of data, obviously, because, well, not just one single light ray is getting into the camera sensor. If you have multiple light rays, yeah.
At any single point, there is a close to infinite amount of light rays like reflecting off of it. So you can't have one light ray.
Correct, but you can decrease the error that you're receiving here right now, because say you can see your camera in the back of your photo image right here. If you have so many light rays hitting the camera, you can get different sort of results.
Wait, sorry, what do you mean by the error?
What do I mean by a light ray?
No, like area of the light I'm receiving.
No, so say right now you have a lamp and it's sort of sending out a bunch of different light rays. It's hitting a bunch of things in the room, and it's also hitting the CD at different angles and different areas, correct?
Yeah.
And that is bouncing and going into the camera. This bouncing and going into the camera is really what's showing recording what the camera is seeing. And because there's so many light rays, this can affect the camera, and you can see a bunch of, you're obviously going to see different results than having just a single light ray.
You need the light rays bouncing off of everything.
Okay. You know what? Let's move on, all right? I wanted to ask you about your diffraction grading. Would you mind going to that slide, please?
This one, I guess?
Yes, the diffraction grading. So this is how you measure the diffraction grading. Okay, so I just wanted to quickly ask, what do you think is the most sort of important part of this phenomenon? Is it like the diffraction, reflection, or is it the yeah? What do you think is the most important part of this phenomenon?
I would say the diffraction is the most important part, because that's what actually allowed me to model it as using the obviously using the reflection gradings equations and ultimately come up with like a solved solution for it.
Okay. I wanted to really focus a little. Can you go back to your experimental setup? I kind of wanted to focus on this a little bit and talk about some improvements. How did you sort of alter the angle that the disc was sitting on? Did you just tilt it manually?
Yeah.
Tilting it manually. And how did you make sure that this tilt was sort of consistent? And how did you measure that tilt? Through like tracker?
No, just using a protractor.
Just using a protractor?
Yeah.
Okay. I guess something I can suggest here is, I don't know, maybe 3D printing a gearbox mount. So then when you turn it, it can turn sort of like the CD to a specific angle. And I wanted to talk about a little bit about the fact that you're using an LED instead of a filament lamp. How do you think that this may affect your sort of experiment as a whole in your data collection?
I don't think it should affect a lot because what white light is a combination of all of the different wavelengths in the visible spectrum. And incandescent or filament and LED light bulbs will both emit that white light. And
Sorry, so you're saying that an LED light bulb is exactly the same as a filament lamp? That it releases the same amount of light, like the same wavelength of light.
It releases the same wavelengths of light.
Well, I hate to say it, but I kind of agree with this because I'll disagree with this because LEDs, especially like your LEDs here, they only emit red, blue, and green, and it's not emitting all sort of the wavelengths of light that can be perceived by human eyes. And I guess we can just move on a little from this. So you mentioned that you use the laser to verify the grading. Would you mind telling me how you got that? What did you get for it, like the diffraction grading?
I just got to prove that I could model it as a reflection grading. And
I see. So you didn't actually solve for the diffraction grading itself.
I did that later on. This is just qualitative. And
yes. So what did you get for the diffraction grading? That's what I'm
like. What do you mean? What did I get? Like what I learned from using a lightweight. Even like.
So what was like theoretical versus experimental diffraction grading?
Theoretical versus experimental
would be with the laser.
Oh,
yeah. So it's like theoretical, maybe like what the product said was the diffraction grading, and then experimental might be what you perceived after doing your sort of laser tests.
Experimental, like actually measuring the
yes, diffraction grading, because diffraction grading is, as you said, diffraction is a key component of this problem. So I was wondering if you knew the diffraction grading.
Yeah, I know it's a diffraction grading, but I don't believe that actually doing experiments surrounding it will be relevant because we can only see like this sort of reflection pattern when it's at a low angle of incidence, which I guess I should have mentioned in my presentation. It's outside the scope of this problem, and I only did it in this case just to show that there is some like relevancy to the geometric like diagrams I am bringing up.
I believe that diffraction grading is very important in this experiment, actually, because diffraction is the key component to this problem. And I think it would have been better if you sort of experimentally determined this rather than using a theoretical. I think you're using a theoretical like constant for this.
Determined what part of the diffraction grading? Like all you're saying is like it would be better if I did more things.
Well, the thing is, if you use theoretical ones and you didn't use experimental ones, there might be different factors that are affecting your experiment and then giving you different types of
what's the difference
perceived
between
light.
Experimental and theoretical diffraction grading?
What's the difference between experimental and theoretical diffraction grading? Is that what you asked?
Yeah. Like what?
I mean, the theoretical one is what you get. For example, you buy a product, you get the diffraction grading, but for experimental, it can be different than what you get on the product page. So then you have to kind of experimentally determine that. Or else if you're plugging it into your sort of theoretical model, it might give you a different sort of answer than what you expect. So that's like me getting friction for a problem and then just using what I found online, right?
Talk about friction, which what?
You know what? Okay, you know what? Let's just move on. I was just giving an example because personally, I think diffraction is really important in this. And I wanted to go back to sort of your CD grading here. Would you mind going back to that? I believe it's slide 19, that you wrote the CD grading. Yes. So this was just, where did you get the CD grading from?
What? I didn't. I made this myself?
You just no, like the 1.6 micrometers. Where did you get that number from?
In slide 11, which we already went over.
Yes.
1.6 micrometers grading.
So this was from, sorry, where is this from? Like, did you experimentally determine this?
No, this is manufacturing information.
Manufacturing, okay, thank you. That's what I wanted to ask. So what do you think is the effect of varying this parameter? How do you think that by changing the CD grading would affect this experiment as a whole?
Okay. So as in any diffraction grading, if you change the spacing between it, it would change this value down here.
So like, what do you think would happen if you increased the CD grading size? Instead of 1.6, let's say it's like 3. What do you think would happen?
It was 3. Then it would decrease the amount of maxima we see. So what this means is that we just see overall like less colors. And so if we return back to this, like if you increase this D, this value is going to go down, but since you can't change wavelength, that N is going to change.
And would you say it would take?
So what this means is that there will be more areas of destructive interference between each.
Sorry, I disagree with this a little bit, because I think that what you're going to see isn't sort of more destructive interference, but sort of more different colors at different angles from what you have originally. If you go to your diffraction equation, you actually just passed it earlier. The D is that one, this one. D is actually the diffraction grading. So sorry, not the diffraction, the CD grading. And by increasing this, you'll see sort of different wavelengths of light at different angles, thus sort of changing your experiment. And I wanted to ask,
and different, and you will see different wavelengths just because that's.
Yes, you will see different wavelengths. Yeah. Yes, that's what I'm agreeing with. And I had a quick question here, but did you have any experimental versus theoretical sort of verification? Did you predict when you would see this green line?
Predict what? No, in general, all I could say was that we can only see at like these very low incidents where the CD is nearly horizontal to where the observer is, and that's
really horizontal. Okay. So did you adjust that? So you did adjust the angle, right? Would you mind showing me the graphs for those?
Just this.
Of adjusting angle? Oh, angle and radiant. I see. Okay, perfect. And what do you think about other parameters, like sort of like the temperature that you're in, or like the angle of incidence? Sorry, the angle of incidence. How do you think the angle of incidence can affect your affect your experiment?
Angle of incidence is just going to be this theta I, which is going to change when you change the angle of the disk. Just because like the angle of incidence is always measured perpendicular to the medium that the light is reflecting or hitting. So like when you vary angle of the disk, angle of incidence will also change. So this graph is also measuring that.
Like, how did you predict?
Okay, sorry, I wanted to go back to a little bit about, we're just going to move on from this, but how do you think refraction is important to this sort of experiment? And do you think refraction is important?
I think that refraction shouldn't have that much of an influence, because all refraction does is it will shift the image that bounces back to the observer. And all this means is that you'll just see like
I agree.
And you'll just see like maybe different colors at different areas, but because like.
Okay, I agree with that. I don't think refraction would be a huge difference, would cause a huge difference, but did you have any way to sort of experimentally determine this, or is this just qualitatively understood?
Qualitatively.
Okay.
Answer. All right, cool. Thanks. So next stage, Andrew. So I believe next stage is concluding remarks by the opponent. Let's go.
Thank you, judges. I think I really like the discussion overall. Although overall, I think that she could have sort of improved on her experimental setup a little bit to vary a little bit more parameters. I thought that her qualitative explanation and understanding of this problem was very well done. And some suggestions I would really give is to sort of have a more experimentally accurate setup rather than having such a wide lamp, sort of like have so many different light rays hitting the CD. You should try and decrease that light rate as much as possible for an accurate reading. And another issue that I found is that I don't think she tested a lot of experimental parameters and sort of key constants that are sort of very important in her theoretical models. This is like such as diffraction grading or the CD, sorry, not diffraction grading, the grading. And sort of, although the refraction isn't as important, I feel like knowing the refraction, the index of refraction would also help more accurately predict her theoretical models. And overall, I think that she should just improve by gathering more data and having a more accurate theoretical model to sort of have experimental verification and predict what happens. Thank you so much.
All right, let's go to the next stage. I believe is the question by the reviewer, correct? All right, reviewer, you're ready. All right, let's go.
All right, so this is directed to the reporter. What purpose did the laser serve in your theory?
What process? Sorry,
Purpose.
Oh, all the laser did was just to show as kind of like a fun fact that like this is like modeling as a diffraction grating does work. And using a laser just helped me better visualize that, even though it was outside the scope of the problem.
So next time, how would you make your viewing angle, the one that you use to phone, like to see the light on the CD? How would you make that more stable if you were to repeat this experiment?
I could use like an actual proper camera tripod instead of a, I guess, CD phone stand. As for getting more precise measurements from varying that, I guess I could, as our opponent said, 3D prints like specialized stands to do that. Yeah.
All right, okay, so this next question directed to the opposition. What is the depth of the pit of the CDs? So like the track depth. All right. Yes, go ahead.
Wait, sorry, was that?
That was for the opposition. So what is the track depth? So the CDs have tracks, right? What's the depth of each of those tracks? All right.
Like
so
2 microns?
Yes, exactly. And follow-up question: when you have a green wavelength of light that is incident upon this, green wavelength of light has wavelength of approximately 500 nanometers, while the depth of the pit is 200 nanometers. How would this influence the green light phenomena?
I believe it's just refraction.
Like
Okay.
slit.
All right.
I believe that
so-
having a thinner slit, and from Young's experiment, it just results in just diffraction.
Okay, so next question is for the reporter. Instead of using LED, if you used a filament, how would you control the amount of light that would be incident onto the CD?
I guess one way to do it, instead of putting a filament over the lamp and reducing total intensity of the light that comes out and reducing like the light you see on the disc, a better way would to like put a sort of cone around the disc so that it limits in what direction the light rays are spreading.
Okay, as an alternative, you could also use a spectrometer, which has a collimator lens and has a slit, which would make all the light rays parallel to the surface of the disc, which would reduce your experimental error. Okay, and so, yes, thank you. Those were all my questions. Thank you.
All right, next stage. Preparation of the reviewer. Minutes. Let's start. Reviewer. Let's try to get our slides up. Okay, Andrew. Start the clock.
Okay.
So I'm from team short children doing problem D, reviewing colored lines, which is problem D. So the objective was to construct a reliable experimental setup to produce the phenomenon, describe qualitatively and quantitatively the conditions required for a green line, experimental and theoretical match for conditions of a green line, and analyze parameters that affect the production of other colors and other diffraction patterns that you observe. So our understanding of the problem is that theoretical analysis, qualitative analysis, geometry and line analysis, angle of reflection, tilting angle, angle of light source and line versus observer, wavelength versus angle of disk. Merits of the reporter are that they qualitatively explain the disk characteristics, why a green line happens, preliminary observations were explained, experiment with glazed gratings was appreciated. Next steps is there to improve their experimental setup to have it become less shaky, consider different light phenomenon and other diffraction patterns, and they provide no theoretical match with experimental data, so do that the next time, and there has been no investigation relevant parameters. So some key insights of the opponent were that they proposed the improvement of the experimental setup, theoretical equations to predict the green line, experimental verification, and possible key parameters. Some of the merits of the opposition's case was that they distinguished the filament lamp and the LED light bulb, and they pointed out the differences. They pointed out uncontrolled measurements. They further discussed the theories, and they outlined the relevance of a CD grating and its shape. So next steps are that they did not point out the poor graphical analysis in the report. They did not point out the lack of measurement tools, lack of precise measurement tools such as a ruler, protractor. So now going on to the valuation. So there was a point raised by the opponent that the LED light bulb only has RGB values, and there's a limiting spectrum seen by RGB values. And the reporter responded that they did not think it would influence. We agree with the opponent that the filament lamp provides the entire spectrum, while RGB provides a finite number, as you can see on the bottom, which is 256 cubed. Next is a point raised by the opponent that many light beams influence the color seen on the CD. And then the reporter responded that the light rays have minimal impact. We agree with the opposition. Instead, just use a spectrometer, which has a collimator lens, which focuses the light on a certain part of the CD, and a covered filament lamp with the lampshade to prevent any light spreading. Next, the point raised by the opponent was that why did you use an LED light instead of filament? And they said that there's no difference. We agree with the opponent. Filament lamp has a different spectrum, and the problem statement says that one must use a filament lamp. And so now for going to next steps, so theoretical. Next steps are mixed physics. For theoretical, the reflection occurring on the CD produces a green line, which I have stated before in the question period. They should also have looked at the track depth, as we did in our presentation. For experimental, they should consider the shape of the CD. For instance, we investigated different parameters such as the sector, basically the angle of the sector that is cut of the CD. And they could have also conducted an experiment using more precise tools such as spectrometer for better angle slit measurements. And that was all that we had to say. Thank you so much for your time.
All right, let's move on to the next stage, which is 2 minutes concluding remarks by the reporter. Let's begin.
I would like to thank the reviewer for a wonderfully insightful last comments on the discussion between me and the opponent. And just as an overview of my presentation, I guess, like I qualitatively defined and observed the diffraction grating on the disk, and also provided some equations surrounding the reflection grating of the disk to show what colors could be viewed on the disk in this in the visible spectrum. And in the discussion between the opponents and I, we first we went over some aspects of my experimental setup that could be improved, and as the reviewer pointed out, some more precise ways of improving the setup could be using a spectrometer to limit the light rays that bounce off of the disk in K-log manner, or to in a manner that increases the error of my experiments. And additionally, we discussed the difference between the LED and the filament light bulbs, which in the end just includes in a difference between the differing wavelengths that the two light bulbs will emit. And finally, we also went over some merits of using modeling the CD as a diffraction grating, and discussed how important or relevant it is in the context of this phenomenon. And also we went through some quick error discussion surrounding the importance of refraction and how that might have affected the data and such. I would like to thank the reviewer for the time, and also quickly wish the opponent another belated happy birthday, Archie.
All right, cool. Let's move on to our next stage then. Just questions from the jury. Let's maybe take 10 minutes, since we have, quite a few jurors. So if you have a question, you can use the hands up emoji, and I will call you, hopefully in some type of order. Oh, Neo has a question. Go ahead.
Yes, I'd like to ask the opponent for your CD. Did you attempt to do this with a filament light bulb?
Yes.
And your filament light bulb was what color?
It wasn't perfectly white light, but it was like a bit dark. It was like a yellowish, orangish hue.
Yeah, because most filament light bulbs being tungsten, and you don't want the tungsten filament to melt, can only get to reddish, orange, yellow, right? And you are saying you managed to cause green light to diffract off your CD?
Yes.
Okay. Okay.
Any other jurors have any questions? Oh, Ali Reza, please go ahead.
Okay, yes, I can ask a question about how the uniformity of this grating pattern on your CD or DVD could have affected the result. Can you elaborate on that a little? Both the reporter and the opponent.
Sorry, what do you mean by the uniformity of the spacings? Like the fact that with every track there's going to be like this indent and with spacing of 1.6 micrometer between it?
Right, the spacing, if it's uniform, then your theoretical model stands. If it's not uniform, which might actually be the case in a real CD-ROM, then how much that would have affected your result? Was it significant, the effect?
If it was, I didn't see it in I didn't observe it visually or experimentally, but it is possible since the tracks are just recorded and they're not always going to be right next to each other. It's just that in most of the case, it's because these tracks are like longer in length. I believe that the spacing between them should be on average 1.6 micrometer, and the non-uniform parts should be somewhat negligible.
Okay, thank you.
Sorry, may I answer the question? You did direct it to the opponent, right?
Oh yeah, you also please.
Okay. So in my experiment, I used the blank CD, and we also experimentally determined the grading. This way, it will have a constant grading and it matched with theoretical, and that's what sort of made sure that our experimental was accurate.
Oh, we have Paulo.
Hi. Yes, well done, both, all three. I have a question for the reviewer. So you quoted this value called the finite number for the LED light, and it was like 256 cubed. I'm not very familiar with that parameter. Can you explain what that is briefly?
Yes, so it's not exactly a parameter, but since for each possibility, for each RGB possibility, you have 256 choices. Overall, if you were to combine all the red, green, blue values, which range from 1 to 250, 0 to 256, that would be 256 cubed. Oh, sorry, 0 to 255. That would be 256 options, and then you cube that for every single red, green, and blue value. So it's 256 times 256 times 256, which would be the result I put in the slides.
All right, cool. Maybe next juror, Shantanu, is that how you pronounce her name?
Yeah, thanks. Shantanu, rhymes with canoe.
Shantanu.
Excellent job, y'all. I have 2 questions. The first is for the reviewer. You brought up this idea of considering the depth between the, I guess the pit depth, if you will. And I wanted to ask for you to elaborate briefly in a few sentences on how this would influence the green light.
So the wavelength of green light, as I said before, is approximately 510 nanometers, while the depth of the track, like the pit, is 0.2 microns, which is 200 nanometers. And because of that, we noticed that the entire one wavelength of green light would not fit in the depth of the pit, and thus would not go exactly to the pit and just reflect off the surface, which is why we occasionally see only a green line on the CD surface.
I see. And do you feel that this was a component of the reporter's analysis that was missed, or do you feel like that was included in their analysis?
This was missed as they did not mention it in their presentation. And if our team were to redo this experiment, we would alter the depth of the pits to see what else would happen, like what other colors or diffraction patterns we would observe.
Sure. And my second question is to both the reporter and the opposer in that order. Again, briefly, since other judges might have questions. With the large angle of incidence, which was addressed briefly by the reporter, I'm curious whether experimentally you found an angle after which you could no longer see the green light.
In general, like they didn't know like green line specifically, but I did know when you stopped seeing just a line and just started seeing the reflection of the light in the disk.
And what was this angle? Do you remember?
It was pretty low at around from the normal. It would be around, I think 20 or 30.
Okay.
Yeah.
That's fine. Thank you. And opposer, I would like just briefly, was your finding of this large angle of incidence, this threshold angle, within the 20 to 30 degree from the normal as well?
Ours is around 20 degrees, yes.
Okay, thank you. I turn it over to other jurors.
Any other juror have a question? All right, last call. All right, cool. Then Andrew, perhaps we can move on to the next stage.
Sounds good.
Score entry. All right. So maybe let's just give the jurors maybe like a minute to finalize their scores. And jurors, when you're ready, just maybe put up your hand with your little hand emoji also. And then so we know that you have your scores. So for the final, we're not going to ask you to do score sheets. So please make sure that the number that is shown on screen is the number that you want to give. All right. maybe to speed things up, we could just ask the jurors that already have their hand up to announce their score. So on my list, we have Clara first. Clara, you want to say your scores?
Yep. For the reporter, I have 4, 0.5, minus 1.5, 4, 4. For opponent, 0.5.
1 second.
2.5, 3, 0. That should be 7.
Can you repeat the reporter score?
Yeah, so 4.5, 1.5.
So 5.
1.5. 1.5.
1.5 in the third box instead of
0.5.
Instead of 0.5.
1.5.
So 4.
Oh no. The box
Yes.
before that. Oh, is that correct? Minus
Yes,
1.5?
that's correct.
Okay, for 4. Okay, cool. And then for the reviewer?
Viewer 1, 2. Oh no. 1, 2.
Oh, like 1.
Not including the first one. 1, 2. 2.5. 1. Positive 0.5. 0. That should be 8.
Yep.
8. All right, cool. Neil?
Okay, my first box is a 4. And my second box is a 2. Third box is a 0. This should total to 7. Okay. For my opponent, my first box is a 1. And then a 3. And then a 2. And then a 1. And that should equal, my math is right, 8. Okay. And finally, my my reviewer, first box is 1, then 2, then 1, then 2, and then 0 and 0. Okay, thank you.
Shita?
Thanks, Jim. So for the reporter, it's 1, 4, 1 minus 1. For a total of 5. Perfect. And for the opponent, it is 1, 1, 2, 3, 0. This should total to 7. Yes. And then for the reviewer, it's 1 plus 1 plus 2 plus 2 plus 1 plus 0 plus 0. So the total should be 7. Yes. Thank you.
All right. It does seem like we are taking quite a lot of time to enter the score. So if you haven't announced your score yet, you can just send a message in chat to Andrew, and then with your sub scores, and then just send it to him, and then he will record it. So we don't want to keep everyone here for too long. So Andrew, perhaps you can turn off your camera and then you could record that on a separate basis. It adds a little bit of suspense towards the end. Yes.
I'm using my own account right now for score entry. So if you want to do the timing, you can log into the super account.
Okay, so then sure, I'll log into the super account then, and then I could run the timing. Just give me a sec. Okay. So let's maybe just take a 5-minute break, and then we'll come back at 5. Let me set everything up.
Yeah. So let's see if it's done by then I can keep on timing if score entry.
Yeah.
Oh yeah, just for the jurors, it would be ideal if you put all three scores at once, or else I'm looking at yours and then 5 other people's and then yours again.
Yeah, sorry, I like tried to hit return and then it sent like one score, not the 3. Like I tried to space it down, but yeah, sorry.
A tip is if you do shift enter, it'll just go down one line.
Thank you, that was helpful.
So Andrew, can I actually start the timing for the next stage when you're still entering score? Is that allowed by the system?
Yeah, it doesn't affect anything.
All right, cool. So then I would like to ask the 3 teams before you take a break to tell me who will be going on stage. So for UTS, MMM, who will be going on stage?
Emily.
Emily, all right.
For MMO.
And for MMO.
From
correct.
UTS,
Yes.
MMM.
From UTS, MMM. And from Short Children, who will be the opponent?
Junior Sun.
And for UTS Shroomskis, who will be the reviewer? Shroomskis? Shroomskis? Guys there? Wow, I guess. Does seem like everyone appreciates a break. So we'll wait for them for 2 more minutes.
So to clarify, there's no time for reviewer comments in the final round, is that correct?
Let's for the
jury,
interest
jury
of time,
comments.
jury comment, yeah, for the interest of time, we can just skip over that.
I also wanted to clarify, are we submitting the score sheets on?
You don't have to submit the score sheet anymore. You can just submit your score via chat to Andrew.
Okay, thank you.
Do we have Shroomskis back? Dave, can you just give them a quick ping and tell them to come back?
Sure.
Wait, sorry, are we announcing the reviewer?
Yes.
Oh yeah, it's Nathan Wang.
All right, submit. All right, so we will, let me stop share and change that to my window. Okay. All right, so can everyone see my window right now? The clock? Dave, can
Yeah,
you
I can
confirm?
see the
Yeah,
clock.
it works. It works.
All right, cool. So we'll skip the preparation then. Well, actually, we'll give you the preparation, and then if you guys are ready, just let me know.
Hi, can I start?
Sure, you may start.
Hi, my
let's
name's
go.
Hi, my name's Emily, and today I'll be presenting problem number E, magnetic mechanical oscillator. So the problem statement reads as follows. Secure the lower ends of two identical leaf springs to a non-magnetic base and attach magnets to the upper ends such that they repel and are free to move. Investigate how the movement of the springs depends on relevant parameters. So the parameters we've identified and investigated today are magnet strength, length of springs, the distance between the springs. And onto an overview of my presentation, I'll be going into an introduction and then experimental setup, theoretical models, which are repulsion and elastic force, as well as dampening, and then key parameter interactions, including magnetic strength, spring length, and distance. And lastly, showing how parameters interact to change the oscillation frequency as we change various parameters. So for an introduction, here's our phenomenon as a labeled video clip. As you can see, we have two magnets with their north poles facing inward, attached to two metal rulers. And when we give one metal ruler an initial displacement and release it, we see that there is the oscillation pattern as follows. So now for our experimental setup, we have the metal rulers. So these are stainless steel rulers with the cork part of the ruler removed, and then the two identical magnets in terms of shape and size attached to the ends of the rulers. And we have both these rulers clamped to a wooden block, which is then attached to a high mass base with a camera on a tripod filming against a grid background to make it easier to track. So the measurement method, we tracked the center of each magnet against time, and we did that for both magnets. And we have a plot as follows, where we see that the oscillation of each magnet kind of interchanges. So when one magnet is at its maximum displacement, the other magnet is really close to the point of equilibrium. So now for our first theoretical model, which is magnetic and elastic force. We assume that the repulsion force between the magnets follows the standard equation. The magnetic force is always directed straight between the two magnets. The rulers follow Hooke's law, and the vertical force components are not considered. So for assumption number 2, this means that the two magnets are arranged so that their poles are along the same axes. And this corresponds to assumption number 4, where the vertical force components are not considered because the two magnets, the magnetic field between them only interacts along the horizontal axes. So these are the assumptions we made for the oscillation patterns that we observe. So for some qualitative understanding of this phenomenon, at equilibrium, we have the magnets mounted on the rulers. And in this case, because they're placed a good distance apart, there is no initial magnetic repulsion between the two magnets. Whereas when we give one magnet an initial displacement and release it, when it approaches the other magnet, there's magnetic potential energy between the two magnets, as well as kinetic energy from the springs. So we see that when on this side of the slide, when the one magnet is falls really close to the other, the repulsion forces point oppositely, whereas the spring forces point in the parallel direction. And we see that in this case, because the energy is transferred between these two methods, we see an oscillation pattern occur. So for basic principles, we used elastic force in a Hooke's law spring. So we assumed that the ruler that the magnet was attached to follows Hooke's law, where x is the displacement from the equilibrium position and k is the spring constant. So for the displacement from the equilibrium position, we used tracker to kind of track that against time. And then for the magnetic force between the two cylindrical magnets, we used an equation from paper. So this is basically the equation, the magnetic force between two cylindrical magnets. The variables involved include the displacement as well as the size of the magnets. So for the combined solution, we used Newton's second law to write the force as the mass of the magnet times, or the mass of the magnet times acceleration. And we see that the force is a combination of the elastic force and magnetic force between the two magnets. And from our previous slide, we can write the elastic force as K times the displacement from equilibrium and the magnetic force as the equation from paper. So we used Python to solve these differential equations because from this equation we can get x. So the x value is the displacement for the left magnet, and then the y value is displacement for the other magnet. So by using Python, we can solve these differential equations, and we can obtain a plot as such. So in this case, we see that at a very close up, the experimental and theoretical does match. In terms of numerical values, there is some deviation. However, our Python model, which was based off our derived equation, was able to model the displacement of each magnet quite well. We see that when the one magnet reaches its peak displacement from the center, the other magnet lies very close, and that's the oscillation patterns that we observe. So for kind of like a macro view of this Python simulation, we see that zooming out from the previous slide, that the Python model is very consistent. There is no damping force, whereas in our experimental, there is significant damping force that kind of reduces the amplitude of our oscillations over time. And so now onto our second theoretical model, which includes this dampening. So this is eddy currents, deformation, and air drag. So basic principles for this theoretical model is that there is permanent deformation because of the plasticity theory. Kinetic energy is converted to elastic strain energy, and plastic strain energy deforms the metal plastically. And this is also irreversible, which means energy dissipated by plastic deformation and stress wave propagation. There's also an equation for air drag that must also be taken into account, as well as eddy currents, because we have the movement of a conductor in a changing magnetic field, which generates current, and this is dissipated as thermal energy. However, because some of the magnets we use aren't very conductive, eddy currents are less of an impact on our oscillation patterns. So for our combined solutions, we adjusted our experimental graphs by dividing our displacement by e to the negative nt, and by doing so we see that this kind of adjusts for the damping. And for varying key parameters, for varying ruler length, we see that as we decrease the length of the ruler, the amplitude also decreases. So in this case, for our experimental setup, we move the rulers lower on the magnet so that when we displace them, they have less like the spring constant decreases because there's less to oscillate as the ruler length decreases. And we see that affects amplitude. The magnetic force isn't as strong of a player here because we kept the same magnets for each of these trials. For varying ruler length, so these are just the plots on separate slides because, as you can see from the previous one, it's not very clear. As you can see, as we decrease the ruler length or the distance or like the spring length, then amplitude decreases. And for varying magnet strength, we see that as we vary the strength for magnet C, magnet B, magnet A. So this is, we have two neodymium magnets here and one graphite magnet. We see that the peaks and troughs that we observed before kind of decrease as the magnet strength decreases. So here are the graphs again. And for varying distance, this is where we vary the distance between the two magnets to begin with. And we see that the oscillation, that firstly, the amplitude kind of stays relatively similar, but then the displacement for each magnet changes. Now, each graph is plotted on a different slide. And in conclusion, we've shown a reproducible, reliable experimental setup. We have our theoretical model for the displacement of each magnet against time. And we have our theory versus data comparison, where we see that the shape of the oscillations is relatively similar, although we weren't able to match the magnitudes accurately. And lastly, we varied key parameters and showed the interactions between changing the ruler or changing the spring's length, as well as changing the magnet's strength and size. And here are references, and thank you for listening.
All right, 2 minutes of questions by the opponent. Let's start now.
Yeah, thank you so much for the presentation. I just have a few questions. I think first of all, on your relevant parameter slide, you talked about like magnetic strength being one of the parameters. So I want to ask, what specifically does magnetic strength depend on?
So like
the strength of the B field, I guess, between the two magnets, what does that depend on?
Oh, well, obviously the distance between the magnets and the properties of the magnet.
Like specifically what properties of the magnets?
The material, the shape, and the size.
Okay, so did you like vary the materials for like the two magnets, because you never like give the dimensions of your magnets on your presentation?
Yeah, so for our first slide, we used graphite magnets, and then for the other ones, we used neodymium magnets. And I do realize that we did not provide like dimension slides or slides about the materials used.
Yeah. Also, like you mentioned, you use like metal ruler as sort of like a replacement for leaf spring, and you mentioned like the metal is like stainless steel, which I believe could be magnetized. So then, I was wondering like, how did you put the magnet like onto the ruler? Like, did you just like, because like they attract each other, you just like stick it on there, or did you like tape it, or like?
We just stuck the magnet onto the ruler because the stainless steel can be magnetized.
I think this might be okay. I think this might be like a bit inaccurate because you're only looking at the horizontal direction. So then you sort of have to make sure they're like horizontally aligned. But then if you just like stick it on there, it's like very easy to like move and then like cause like disturbance and whatnot. So that is a point that I want to bring up. And also in your presentation, you talk about like magnetization of the magnets. How did you find that? How did you find that number?
So we didn't actually find it experimentally for our Python plot. As you saw, we just replaced it with a constant, which is why the values are, or which is why our theoretical and experimental graphs are not aligned.
Okay, all right. Thank you so much.
Thank you.
All right, next step, 3 minutes of preparation of the opponent. Could the opponent pull up their slides? All right, you can start whenever you're ready.
Yeah, I think I can start now. All right.
Go ahead.
Okay, so hi everyone, my name is Oscar Sun, and so today I am opposing problem number E, magnetic mechanical oscillator. Let's just revisit the problem statement. The problem states that secure the lower ends of two identical leaf springs to a non-magnetic base and attach the magnets to upper ends such that they repel and are free to move. Investigate how the movement of the springs depend on relevant parameters. So for this problem specifically, in order to have a successful report, I identify the following tasks. Task number 1 is to construct a reliable experimental setup to reproduce the phenomenon, such as the coupling of two moving magnets. Task number 2 is to theoretically model the leaf spring bending, magnetic attraction, and the damped oscillation of the two magnet system. Task number 3 is to arrive at a match between theoretical and experimental data. And the last task is to identify and investigate relevant parameters, such as like leaf spring properties and the magnetic cylinder properties. So here is a summary of Emily's report. In her report, she has two theoretical models, which is the first one being magnetic and elastic force, the second one being dampening. And she conducts experimental verification on the horizontal position versus time. And later on, when she introduces damping, she also has damping adjusted graphs. And then she also investigated how like the length of ruler might impact the like horizontal oscillation of the two magnets. So here are some merits and next steps for her presentation. She, like some good things in her presentation, she has multiple parameters considered, for example, the magnetic strength, the length and frequency, and she has thorough theoretical models. I think her coverage of the magnetic force, elastic force, and also damping is pretty comprehensive for this phenomenon. She also has some varied parameters such as the ruler length, and she has some well-explained graphs, and showcasing that there is some sort of theoretical and experimental correlation. However, I do think there are some areas in which the presentation can be improved on. First of all, for the experimental setup, there is going to be instability and deflection of the ruler during oscillation is not really like controlled across different trials. And she lacks experimental data processing. Like she kind of just put the oscillation side by side and then consider that a correlation between theory and experiments. She also didn't provide explanation on why like the theoretical and experimental don't match. And more specifically, I'm talking about like the amplitude for different oscillations and how like the time scale doesn't really match with each other either. And last but not least, she also lacked analysis on the properties of the ruler as well as this like spring coefficient that she mentioned in her theoretical model. So here is an overview of our discussion. First of all, I want to talk about improvement in experimental setup, better control when it comes to initial displacement and measuring magnetization, which as Emily said, she just kind of like fit the magnetization using her Python code. And my second point is to like look more into the different types of energy that's present in the system, because she did mention it in terms of like the damping model. And then I want to talk a bit about the coupling between the two magnets and what factors specifically is causing them to be connected by this quote unquote a spring like between them. And last but not least, I want to address like some theoretical and experimental discrepancy in her graphs and how that can be improved. So with that, I'd like to invite the reporter to a discussion.
Yeah, I'll just pull up my slides. So yeah, where do you want to start?
Can you like start from the beginning?
Yeah, sure.
Okay. Yeah. Okay, can you go to slide number 2, which is your relevant parameters slide?
Mm-hmm.
Okay, so I believe like I think all those parameters are really relevant to this problem, but I think specifically for like the ruler or the leaf springs that you use, can you identify a few properties about the leaf spring that might make it onto this page, the parameter page?
Yeah, so mainly we varied the length of the leaf spring, so like where we place the magnet on the leaf spring, but we didn't investigate the properties of the leaf spring itself.
Is there anything beside the length of the leaf spring?
No, we only varied the length of the leaf springs.
But theoretically, what do you think are like some of the relevant parameters for
I think
this?
the magnetization of the leaf springs definitely should be considered.
Okay.
But in terms of materials, we only were able to access these.
Yeah, I partially agree with what you just said. I think like because you use stainless steel, so the magnetization of the leaf spring does become like a relevant issue in this scenario. for me personally, I use like aluminum, which cannot be magnetized, so that I don't need to take that into consideration. So I think the magnetization is a parameter for the leaf spring, but it's not a universal one. Some other things you can consider is like the width and thickness of the leaf spring. They're just as important
That
as
should
the
change the spring constant.
yeah, that should change the spring constant, but the spring constant is a part of your like motion,
Okay, yeah.
right?
We
And
were mainly we tried changing the spring constant by changing the length of the magnet, length of the ruler. So that was our main way of varying spring constant.
yeah,
Although
I
we were
think
able to find it.
yeah, also I think you forgot to like consider like the property of the leaf spring itself. Like it's not just magnetization, there's also like Young's modulus, like how hard it is to bend the leaf spring. So I think that might comes as like important for the leaf spring as like a parameter. Okay.
But in our theoretical model, we did model it as a Hookean spring. So that's why we basically only varied the spring constant by varying length.
Yeah, I understand the difficulty, but like I actually find a relationship between like the horizontal force and displacement. So F equals to kx. I actually find an expression for k in terms of like leaf spring. It is equal to EBH cubed divided by 4L cubed. So then that just like combines like different properties. And if you make some like assumptions, it is possible to find such an expression. Can we go to slide number 5? Yeah, okay. In your video, how like you didn't have any marking in the background. So I was just wondering how do you like, first of all, how do you calibrate it and how do you control the horizontal displacement, like 1 centimeter, 2 centimeter, and so on?
Yeah, in the background, we used grid paper. So that's how we calibrated it in Tracker. I don't think you can see it very clearly, but there is grid paper in the background. In terms of the initial displacement, we kind of approximated that one to, so we measured the distance between the magnets and in Tracker, and that's how we calibrate like the initial position. But in terms of pulling it back, we think that because it's like an oscillation pattern, however much we pull it back, it would still fall into the same pattern every single time. So that's how
Okay. For experimental procedure, I just like want to point out something. I think like the pattern is definitely the coupling between the two like magnets, but then I think initial displacement sort of like determines the amplitude of like their oscillation right from the start, right? So then like if you want to control that, and if you want to like later on you have like experimental graphs that like doesn't have matched amplitudes, so then that basically like sort of like is saying that you didn't control the initial horizontal displacement. So I think that is something you should take into consideration for better comparison between like theory and experiments. But all good. Okay, let's move to slide number 12. Okay, so in slide number 12, repulsion force between magnets follows standard equation. Could you just remind me what is this standard equation?
Yeah, equation from theoretical. It's theoretical equation, so it's this one. Oh, sorry. Here, we use this equation for the magnetic force between two cylindrical magnets.
Okay. So now we're on to slide. Okay, all right. Can you go to thank you for answering that question. Can you go back to slide number 13? Yeah, when you're like explaining the sort of the coupling between the two magnets, and then you're saying like if the magnets are like a good distance apart, there won't be like the coupling motion happening, or it's like very hard to like start this coupling motion. So like for your setup specifically, could you like tell me like what is the distance that like basically will make this experiment not work?
Okay, so I think in terms of the distance between the two magnets, we were constrained by the wooden blocks that we used. So I think initially we had it at most at like 5 centimeters apart, and there was no repulsive force.
Okay.
We didn't determine like a point of like where there is a spring, like there's repulsion between the two magnets.
Okay. All right. Thank you so much. Can you go to slide number 14?
Sorry.
Actually, this slide, yes, slide number, this slide. So then you see like the bottom equation, there's like a relationship between like f of x and then whatever is in like the square bracket, right? I assume like those are like length values that you can like measure. So then from this equation, do you have like an idea of how you can possibly measure the magnetization? Just looking at this equation.
What do you mean by measure the magnetization? Just like measure the magnetic force?
Because you said like magnetization, like you fit that in your Python code, and so I was wondering like, is there any way you can like experimentally determine it? And then I think like this equation can be illuminating when it comes to like. Yeah.
We can either use the Pascal sensor to determine the magnetic field and then use that to find force, or we could. One experiment that we tried to run is that we placed one magnet like on a scale and then we dropped one magnet at various distances above it, and then on the scale read like if there were any changes in the force experienced on the scale.
Yeah. Okay. So yeah. Okay. So
That's how we found the relationship was 1/r⁴.
Okay. Yeah. So I think like one of the ways you can do it is like using a Hall sensor, and then for the same magnet, you can just like secure it and then place it like various distance away. So then that will give you like many different like values for whatever is inside the bracket, and then you can also measure the magnetic field. So you should be able to get the magnetization for the same magnet. Okay. My next question for you is, for like all the magnets of the same material, you use like NeoD magnets, right? Do you think they have the same magnetization, or do you have to like repeat the experiment that I just mentioned for each
magnets
magnet?
of different strengths, so we would have repeated the experiments for different magnets.
And why do you think like magnets of the same, for example, there are two magnets of the same dimension, same material, everything, but like why do they have different magnetization?
If it's same material, same dimension, everything, then no, we wouldn't. But if it were different material, different dimensions, then we could just scale the magnetic field.
I actually disagree with what you just said. When I was doing this experiment myself, I had like same magnets, like when it comes to dimension and material. However, I use like a Tesla meter to measure the magnetic field, and they are shown to be very different. And I think magnetization actually depends on like the history of like whether it has been placed on like a magnetic field before as like a ferromagnet and whatnot. So then I think this procedure is necessary to like repeat for like all the magnets in order if you want to figure out the magnetization.
So if you had like two magnets of different magnetizations or different magnetic force from each, did you observe a different oscillation pattern? Like was one side did one side have a higher amplitude than the other, or did you only track one side of the two leaves?
For my experience, I actually use like all the magnets with the same magnetization, actually like sort them. So then like same with your experiment, like magnets are identical. So yeah. Okay, all right. Can you go to slide number 17? Yeah, I have like two questions for the site. You can see that for your horizontal position, like your theoretical graph, your amplitude is 0.02 meters, which translates to 2 centimeters, but that doesn't match with whatever is on the experiment side of your equation, right?
So, for when we plug this in Python to get the theoretical model, like Python had difficulty focusing on the time units, so that's why we had to model it with different time units in terms of the horizontal axes. So I think that's why the two are on severely different time axes.
But then if that's your approach to like sort of like finding like a match between experiment and theoretical, I think this is kind of like being trivial because you're just sort of like seeing the shapes. Like, yes, I have like a coupling theoretical shape, and experiment, I get the same shape. So then like I would just call it like a theoretical experimental match. Is that a little bit problematic?
Well, yeah, I think given more time, we would have been able to scale for the actual values themselves, like plug in the values into our force equation. But in terms of this, I thought that just by showing like how the coupled oscillations between the forces, showing that the amplitude is how it looks is sufficient.
Okay, thank you so much. Can you go to slide number 21?
Okay. Sorry, my laptop's slow. 21. Yeah.
Okay. Did you try to scale it? Why did you divide it by e to the power of negative nt?
So this was kind of like adjusting to kind of remove the dampening.
Okay. Can you go back to slide number 20 then? But okay. Yeah. Okay. So like, what is the insight into looking at like the different energy loss of the system? Because they're actually not included in your equation. Like it's not present. So why do you look at it?
We just wanted to qualitatively explain which energy loss, which factors can contribute to energy loss. Whereas in the next slide 21, we just included it all as one coefficient, which is n, which had a value of 0.03. So because it was difficult to model like the permanent deformation, the eddy currents, and the air drag, so we just wanted to qualitatively explain it.
Okay.
Thank you to the opponent and the reporter. Let's move on to the next stage, which is opponent summarizes the discussion. Let's begin.
Yeah, first of all, I'd like to thank the reporter as well as like all the jurors for this like insightful discussion. I really enjoy like this exchange and sort of like talking it out on this problem. So then when it comes to our discussion, for sure, we talk about like how to better control the experiments, specifically like when it comes to like the magnets and the rulers, what are some like the parameters like impacting both. And when it comes to magnetization, I recommend using like a Hall sensor too. And there's also like different magnetization even for the same magnets. I think that's something the reporter should be aware of when she conduct like different experiments, because then there would not be symmetry in like this system. And also like we look into sort of like the different energies like present in the system and how like they damp from like the total energy. And we also address some like theoretical and experimental graphs. I am glad to hear that like the theoretical graph is like from FIT, because because I was confused by like sort of like the scale and like the amplitude and whatnot. But overall, I really enjoyed talking to the reporter, and hopefully the reporter learns enjoy this discussion as well. Thank you so much.
All right, next stage is the 3-minute question from the reviewer to both the reporter and the opponent. Let's begin now.
Okay. All right, sure. I'll just start. To the reporter, can you give an order of magnitude estimate for the mass of your magnet?
It was around 60 grams.
Around 60
Wait,
grams?
In terms of for the 3 different masses we used. Wait, sorry, I have the values.
Can you give like a estimate for like the percent of like the mass of the system which is in the magnet, like versus the spring? All right, that's okay. We can move on. To the opponent, what do you believe?
Sorry, it was 6 grams. It was 6 grams. It ranged from 6 to 10 grams, and then we had another magnet that was 50 grams.
And then what was the mass of your rulers?
All
right, that's okay. We can move on. To the
30
opponent,
to 40 grams. 3 to 4 grams.
3 to 4 grams. Okay. To the opponent, what do you believe is the primary source of damping in the system?
I think there are 2 like sources of damping in the system. The first one is like aerodynamic drag, and the second one is like eddy's current. But I do believe that eddy's current is like the most significant form of damping.
Current. Okay.
Yeah.
To the reporter, do you agree? What do you believe is the most important source of damping?
I think it's a combination of the eddy currents and air drag. But yeah.
And to the reporter, how did you vary the length of the spring? Did you vary like the point where the spring is like at the ruler is attached to the block, or did you just vary where the magnet is?
We varied so we varied how far it went from the block, so we moved it down. Yeah. So like we moved the 2 rulers lower on the block, so that we clamped at the lower.
So the magnet was always at the tip.
Yeah.
Okay. To the opponent, what do you believe the effect of changing the length of the spring is on like the motion that we see?
I think if you change like the length of the spring, that is going to like if the length of the spring is longer and then you use like the same sort of like horizontal force applied to it, that will like result in a higher amplitude of oscillation when you release the magnets from rest.
Greater amplitude. Okay. All right, and then to the opponent, what do you believe is the most important parameter that the reporter did not vary?
I think the most important parameter that the reporter did not vary is probably magnet sizes. At least like in my impression.
Size. Okay, thanks. Yeah, and then quickly to the reporter, how did you numerically solve your? Actually, never mind. I think we're out of time.
All right, let's move on to the next stage, which is 2 minutes of preparation by the reviewer. All right, let's move on to the next stage, which is the reviewer takes the floor. Reviewer, you can begin now.
Right. Hi, my name is Nathan Wang from Team UTS Shrimskis, and today I will be reviewing problem E, magnetic mechanical oscillator. I'll begin with a summary of the report. So as for the theoretical side of the report, the reporter talked about the magnet characterization and modeled the force between two magnets. Then they then went on to discuss their Hookean spring leaf spring model, where the force is proportional to displacement, and then they talked about damping and the sources of damping, and they were able to sort of combine them all three models by like using a coupled oscillator equation and then numerically solving this in Python. As for their experimental account, their setup included two magnets attached to vertical steel rulers, which were allowed to oscillate. They varied parameters, including magnet strength, spring length, and separation. A review of the report, some of the pros, that they were able to replicate the phenomenon and observe the motion described by the problem statement. They had a controlled experimental setup. They varied magnet and spring properties and investigated their effects. They solved their coupled differential equations in Python and very key parameters with experimental verification. As for some cons, I feel like they had an insufficient qualitative explanation. I was a little bit unclear with the negligible magnetic force at the equilibrium, which sort of contradicts with their theory where the magnetic force depends on the position throughout the entire motion. Thought the motion was really tracked and could have like had a more concrete way to track the springs. The magnetic force was not verified. The force analysis on the system was a little unclear what they meant by mass, whether that meant the mass of the magnet or the mass of the leaf spring. The damping was not thoroughly investigated. Like they brought it up, but didn't like thoroughly investigate like how that would affect the motion. And there was a lack of direct comparison between theory and experiment. I also think there's a lack of physical insight to the solution that they presented. They sort of just put it into Python and then outputted a solution. Would have been nice to see like some actual physical insight into why the solution is what it looks like. As for the opposition, they talked about improvements to their setup, energy, coupling, and deviations between, I should say, experiment and theory. As for review of the opposition, they brought up some very relevant criticisms in their speech, such as the experimental instability with the tracking, lack of direct comparison between theory and experiment, and the fact that all the parameters were fitted. They also added some points like the magnetization of steel and the natural frequency of the cantilever. They had their own improvement suggestions, such as measuring magnetization by like using a Hall effect sensor, and they briefly discussed energy loss at the end of the discussion, which I think is very important to the problem. Some of the cons for the opposition, I thought that there were some irrelevant points, such as like the change in magnetization over time. The second, I feel like they could have incorporated more of their own opinion in the discussion rather than just asking questions. I thought there was a lack of comment on the physical insight of the problem, and I disagree with their idea that the most important source of damping is eddy current. I feel like other like air resistance and like elastic deformation is more important. They first discussed varying parameters such as properties of the spring. The opponent said that they need to be further investigated, and the reporter said that the length of the ruler is most important. I agree with the opponent that the properties of the spring need to be further investigated, and like such as changing bending moments. They also talked about the force between two magnets. The opponent said that there needs to be a way to experimentally determine the magnetization, and the reporter agreed. And so I agree with both the reporter and the opponent that this should have been done, and that this could have been done by varying the distance and measuring the force and field. They also talked about the magnetic field over time. The opponent said that the magnetization of the magnet depends on the history of the magnets, like sort of like the alignment of the magnetization. And the reporter said it does not affect the motion path very much. I partially agree with the reporter. Like, yes, magnetization does change depending on the history, but there's minimal impacts. They lastly talked about energy loss, but we agree with the opponent that it needs to be further investigated.
All right, let's stop the presentation right here. Let's move on to 2 minutes of concluding remarks by the reporter.
Yeah, so both the opponent and the reviewer brought up really good improvements that I can make to this presentation. But in terms of my experimental setup and the tracking method, I think that I was able to quantitatively explain as well as show some trends in very key parameters. For the future, I will definitely look into characterizing the magnets better. So this would be using the Pascal Hall sensor in order to measure the magnetic field away from each magnet. But our method of kind of dropping the magnets at different heights in order to see the repulsive force between them, it gave us a good understanding of why the relationship between force and radius was, or distance between the magnets was 1 to the 4. And another thing is that there wasn't much discussion around the springs that I used, but I think that because we were able to vary the spring constant just by sticking to the 2 aluminum rulers, I think that that was kind of a good way of seeing how the spring constant could impact the oscillation as well. Yeah, so because we use stainless steel, 2 stainless steel rulers, and we did manage to vary the magnets used, so that also gave us another parameter to vary. And we agree with the reviewer that the history of the magnets shouldn't really matter, that the interaction between the 2 magnets is solely along the horizontal axis as we examined, because the displacement and the force between the 2 magnets is mainly along the horizontal axis. And thank you for listening.
All right, let's move on to next step, which is question of the jury. So again, I will just call up whoever that has their hands up. Anyone wants to ask a question first? All right, so I see a hand from Ali Reza. Please go ahead.
Okay, this question is for the reporter, and opponent and the reviewers can also talk about it. Does it matter if your system, this pair of magnets, are oriented toward north-south or east-west? Do you think that would have any effect at all?
I think I can answer this question. I do, like, I understand the intent of this question is to sort of like investigate like how like the Earth's magnetic field might cause an impact on this phenomenon. And theoretically, like they should weigh in terms of this experiment. But like when I do like my setup in like a multiple different like tables and like multiple different locations, I didn't observe like any changes when it comes to like same magnets, same rulers, same initial displacement. When I track my data, there's no difference between like my data. So I think for your question, experimentally, they can be, the Earth's magnetic field's effect can be ignored.
I think that if you did rearrange the magnets to have them like, instead of pointing like this, like that, I think that it would have a slight effect, because obviously the magnetic field strength would change, as well as the perhaps the direction, depending on the shape of the magnets that you start with.
I agree with Oscar. I think the effect of the Earth's magnetic field is like negligible. It's only like 0.5 Gauss, while like the field from the magnets is like much higher. Like I know the ones I use were like the field could like go to like around like 600 Gauss.
Okay, thank you.
All right, so next, Neil, could you please go ahead?
Hi, so my question is to the opponent, Schwartz children. So you mentioned earlier that your magnets were of a different magnetization, that you compared them, right? Okay, now knowing that you compared them, what did you do so that you could adjust for this potential inconsistency?
Yeah, okay. So like at the start of the story is like one day I was like using Tesla meter to measure the magnetic field for like 2 identical magnets, but then one returned like something like along the line of like 130 microtesla, while the other one's like 200 Tesla, microtesla. So then I think like there's no other way to explain this besides the magnetization history and whatnot. So then what I did is like I like measure all the magnets that I have and then sort of like group them based on like similar similar like magnetic field when I measure them. Like so I like I group them based on their sizes, and then within the sizes, there's going to be different like magnetic fields. Of course, I do think that for like, for example, something that returns like 126 microtesla and something that returns 140 microtesla, the magnetization is going to be different, but they are closer, like they are like less significant in my experiment when it comes to, for example, 126 and like 200 something microtesla.
And if the difference was too large, you saw a wildly different motion?
I only use like the magnets that I grouped together. So then I actually didn't investigate the ones with like different magnetization, but I do believe they will have like very different, like they will, yeah.
Okay. Okay.
Okay. Next, maybe Yue Shu. Please go ahead.
Okay. I have a question for reporter. Great job, Emily. I like your presentation, and I'm glad to see you that you did the simulation by Python. I'm just curious about what's the package that you used in Python to do the simulation?
The reporter
I use SciPy and but yeah.
Sorry, can you say again? I didn't hear.
I use SciPy and NumPy and
okay. I see. Thank you.
Any other jurors have any questions? Yeah, please go ahead.
Right. So my question is to the reporter and opposer in that order. And you can be brief with your answer since time is precious. But if you wanted to maximize the coupling between the two springs, how would you adjust the relevant parameters? Reporter first, please. And you don't have to give a quantitative, but a qualitative will be fine.
First, I would put the two leaf springs close together, as well as decrease the length of the spring.
I would actually like increase the length of the spring while like making sure that the magnetic field of the magnets that I use are like the strongest according to like my measured values from the Tesla meter.
So I would increase the length of the spring to have a bigger spring.
I see. Thank you.
All right. Any other jurors have any questions? The last call. All right, cool. Then let's finish our stage right here then. Then please send all of your scores, including your partial marks, to Andrew.
Yep.
Andrew, are you there? Yeah. Okay. So Andrew will note down the score, and then we will just I'll go home, and then I'll time the third stage as well. So let me. Okay. I'm gonna. Okay, so I'll go to stage 3. Yeah, so for stage 3, the problem is Ponyo's heat tube. So Charles children, who will be the reporter?
Using Dong.
Okay. For Shroomskis, who will be the opponent?
The opponent's Daria Piku.
Piku, okay. For MMM, who will be the reviewer?
Sterling. I'll be reporting.
Sterling. Oh,
I mean reviewing.
Reviewing, yes. All right, cool. I will submit. And then first you can send your scores to Andrew. We will perhaps just take like a very short break. The teams can take a short break too. We'll start at 6. Okay, I'm gonna turn up the timer. Okay, and at 6, hopefully everyone will be back. I'll call everyone and then we'll start the timer. All right. All right, everyone. This is we are at 6 p.m. So we'll start the third stage very soon. So I'm gonna start the timer for the reporter. Are the three teams all here?
Yes, the reporter team Short Children is here.
About opponent?
UTS Shroomski's, yeah, opponents.
Right, reviewer, MMM. MMM, anyone? All right, hopefully they get here before the presentation starts. And another reminder to the jurors that when you're giving scores, please give a integer score. Okay, so all of our final scores are in integer. All right. And Andrew, you can also make sure that all the scores that you get are in integers. If there are any decimals, you can just contact the jurors to make them round. Okay, you can like message them on Zoom. Yep.
Hi, I have a question.
Yes,
So-
please.
Oh, just.
Yes, Grace.
Yeah, so for the marking, do we need to round up for every sections or just like the total mark for each person?
So final mark will be an integer. For each section, you could do whatever you want.
Okay, I see. Thank you.
Just to check, is MMM here? Anyone?
Just to check, can everyone see my screen?
Yes, we can see your screen.
I'm wondering if I can start now.
Yes, you can start now. Whenever you're ready.
Hi everyone, I'm Lily from Team Short Children, self-presenting problem letter I upon your seat 2. The problem statement says that a glass tube with a sealed top is filled with water and mounted vertically. The bottom end of the tube is immersed in a beaker of water and the short segment of the tube is heated. Investigate and explain the periodic motion of the water and any vapor bubbles observed.
So some of the parameters that we think are important to consider are first the heated segment length, the length of the tube, the width of the tube, the initial temperature of the water bath, and the power input for heating. This is the overview of my presentation today. First, I'll be recreating a phenomenon, then I'll be going through my experimental setup, and then I'll talk about my theoretical model, discuss about my key parameters and interactions, and finally conclude with my research. So looking at this phenomenon video, we can see that there are bubbles formed here through the wires heating from the power supply. And due to the buoyancy, the bubble will continuously float. But however, when it expands, the bottom of the bubble touches the colder segment of the tube, which condenses here. And this caused the bubble to half condense. And that's why we see the bubble disappearing halfway. So my experimental setup can be explained by first having the tube mounted vertically, being filled with water with no air bubbles accumulating at the top in the beginning to fulfill the problem statement. I have thermocouples and thermal adhesives stick onto the tube itself, so I can have accurate measurement of different position on the tube and the temperature. I also have a thermocouple stick into the beaker itself, so I can monitor the water bath temperature as well. And lastly, I have a power supply that allows me to change the power input that's given to the wires. Having a close up at the setup here, we have a pulley system that allows for close contact of the wires on the tube. As we can see the colors here, although the exposed wires are turning color, but the ones that's on the tube is entirely on the tube. That's why we don't see any color change here. Some experimental measurement tools that we used are first the thermocouple thermometer for reading the temperature and a beaker for volume measurement. Going to my theoretical models, we'll first be analyzing the dynamics of the system. We define the geometry with the diameter of the tube and surface tension of the water. Some assumptions that we hold are first, the impact of water-based dye is negligible, the water evaporation from the beaker is negligible, and the heat loss to the environment through water bath and beaker is negligible. So first, we would describe the motion of just a bubble rising in liquid bath through natural convection itself. In this case, we don't consider the 2BI, it will come later on. So we can define beta as the volume expansion coefficient, which is the variation of density with temperature. And we can approximate the change in density as following, which includes the density and the fraction of a volume change that corresponds to temperature change. And because we know that the buoyant force is directionally proportional to the density difference, this allows us to better understand the buoyant force in this case. So considering buoyancy and viscous forces acting on a drop itself, the Grashof number can be expressed as following, where we have balanced buoyancy and viscous forces. Now, having the real natural convection of the heated region to come into play, we consider the Rayleigh number that drives the natural convection, which in this case, calculating using water, we can see that the Reynolds number is 10 to the power of 9, which is greater than 10 to the 8, implies that the strong presence of convection in our system. And the ratio of conductive to convective heat transfer can be expressed using Nusselt number, which is approximately 685 in this case. Being greater than 100 implies convection is dominating over conduction in our system. Now, adding the two band, we have considered capillary force and the drag force. So we can see that the scaling ratio of drag and capillary force can be deduced as following. We will consider the capillary number and the dimension of the tubes, which will be discussed later as our parameters. There is a pressure drop coming to play as the bubbles form and disappear, as we mentioned earlier in the phenomenon. And as the bubbles form, the pressure inside of the tube increase, pushing out pushing the bubble and causing an increase in the water level. And then as the bubble disappears, the pressure inside of the tube will decrease, causing a contraction back inside. And this will lead to a decrease in the water level on the beaker. So theoretically, when the formation and fading of bubbles are considered, the pressure constantly changes, and we should experimentally see oscillation on water level, which in this case, we do see it. As you can see, the pulses represent the oscillation of the water level in the beaker. Moving on to our theoretical number 2, we'll be discussing heat exchange in the heat region. So first, we define the geometry as following, where we consider the temperature, the mass exchange, the volume, and the mass of vapor. Some assumptions are hold the same as the theoretical model 1, except this here we add that liquid-gas interface has saturation temperature, meaning that the gas is at the interface, the gas is at its boiling point. So we will start with characterizing our system. The rate of heat loss after the empty tube reaches thermal equilibrium can be expressed as following, where we consider that this is the heat transfer coefficient, since after the tube reaches its thermal equilibrium, all the power that we import from the wires to the tube will directly become the heat loss. So that's how we consider the system characterization. And in order to test this, we have a dry tube that's not immersed in a liquid beaker, and it does not have anything inside of the tube. We can use a thermocouple to accurately measure the 6 positions marked on this tube. And here is our final result of the system characterization. As we can see that as we increase the power of input from the wires, there is a noticeable increase in the temperature, in the equilibrium temperature. And for 40 and 60 watts specifically, we can note that they're very similar and there's no significant increase comparing to the rest. This is because at this point, the tube has already kind of reached its thermal equilibrium max. And so adding external heat power to it is not necessarily continuing to heat it up, but instead most of the heat is just directly being the heat loss. So now we can see that temperature increases as we get closer to the heat source, which also matches with our previous theory. Now discussing the heat exchange with regards to the fluids, the heat exchange in the liquid can be expressed as following, which we consider the change of temperature in liquid with respect to time, and we consider all the position in which the temperature of the liquid may change. And the temperature distribution along the inner tube wall can be described as following by using the 1D thermal diffusion equation. The phase change in this system can then be expressed as the following, which here we are taking the integration of the top of the bubble to the bottom of the bubble, and we consider the temperature and the pressure along the bubbles. Some experimental results that we can get from here are we can see that as we increase the power input, we have significant increase in frequency of the oscillation. And this is fundamentally because we're changing the temperature of the tube and it's changing the heat exchange system. We can see some amplitude differences. However, because if we show an appendix, it does fall all into their error bars. And if we look at the side, the unit is about 10 to the -2 centimeters. And then that brings us to 0.02 centimeters, which is very minimum. And we can conclude that change in power doesn't fundamentally cause immediate change into the amplitude, because it fundamentally only changes the frequency of the heat generated, doesn't change the segment or the size of the bubbles. Some other experiments that we did are, for example, we varied the temperature of the initial water bath, in which we can see that as we increase the initial water bath temperature, we have an increase in frequency as well. And this matches with our previous theory of temperature difference as well, because the condensation is not that cold anymore. That's fundamentally what we're trying to look for. And now moving to our last theoretic model, we'll be discussing the superheated vapor at the heated region. So assumptions hold true as the first and second theoretical model. As we define geometry, we still consider the mass, volume, and mass exchange rate of vapor. And moving on to the theory of superheated vapor, we would first like to define the superheating as to it happens because we're heating up a homogeneous substance, and the glass tube is very clean, so there's no nucleation site, and thus we can conclude that we do have superheating region existing in our system. So the thermal energy of vapor can be described as following, where CV is the vapor site specific heat at constant volume, and by rewriting this thermal energy equation, we can get the equation of the energy equation of the entire system, and we can see that this term right here is fundamentally just this term. It's just another way of writing it using heat transfer coefficient and the length of bubble in the evaporator. So it's considering the heat transfer in this place. Now, some experimental demonstration, we can see that in here, the bubble has already been created due to the evaporation from previous heating. And we can see from here that the heated region of the gas specifically is gradually getting above 200 degrees Celsius, which is reaching its superheating phase. And then we can see that the capillary force is not enough for it to entirely go up specifically to contract the water back up to the level. This is because this region of the water is significantly colder than the rest. So it's relatively condensed here, and there's nothing enough to heat it up and bring it back up using capillary force. And that's the fundamental point that we're proving with superheating. So some further insights that we gained from doing experiment is that we see after running the experiment for a long time, we see some accumulated gas at the top of the tube. And some of the reasoning behind that, so we believe, are first because the pressure of the pushing out and extracting in is not the same. And sometimes when we have very big air bubbles, they will exceed the tube itself. So when we contract in, there's some air is contracted back in, which brings some air bubbles that's flowing to the top. And we also consider the dissolved gas and the turbulent and laminar flow of the gas bubble in the tube. So some key parameters that we vary are power, length of tube, initial temperature of water bath, length of heated segment, and the diameter of the tube. In conclusion, we would like to say that the input power is the most relevant parameter to this problem, while other parameters like dimensions of tube, initial temperature of water bath, and heat segment length have an impact as well. Periodic vapor bubble occurs through the boiling of water caused by segment heating, and higher heat exchange leads to greater frequency. So here are our conclusion with our graphs respectively, and thank you for listening.
All right, let's move on to the next step. 2 minutes of questions by the opponent. We start now.
Okay, thank you so much for that report. First, I want to ask, did you calibrate your heat measuring devices, so your thermocouples and thermal cameras?
Yes. So for our thermal camera, we initially calibrated it with a certain object that we considered the temperature of using other measurements.
Okay, so you calibrated them.
Yeah.
So did you only observe these Taylor bubbles, so the long bullet-shaped bubbles, or did you also observe any spherical bubbles?
There were small spherical bubbles in the beginning, and if we see the phenomenon video, it gradually increases in size and develops into the Taylor bubbles as the process of evaporation continues.
How much power did you input into the system?
We varied from.
Please.
Sorry. Oh, we varied from. We vary from 10 to 60 watts, and we realized that it's better to observe from anything from 15 to 20 watts as a minimum, because from 10 we can't really observe anything that's periodic because it takes way too long.
What is the T in your Grisham number?
Sorry, what's the what?
Term?
Do you mind if I go back to my slides?
Yeah.
Where is this one? I think you're talking about the temperature difference, but just to make sure where is it? This one?
Okay, that's the temperature difference. And what is T infinity?
Oh, that's the environment temperature.
Environment, okay. Thank you. And what were your tube dimensions?
Sorry, two dimensions is taken with respect to the bubble length itself and the the radius, but we take the 2 dimension of that.
Okay, so what was the diameter of your tube?
The diameter of tube is 0.5 centimeter. Yeah.
Okay. Did you observe any drop off where the phenomenon stopped occurring?
Not really with the time segment that I considered, but because we mentioned that there is accumulated gas, so we do say that if we have it run long enough time, the accumulated gas will gradually increase, and that will eventually change the overall system.
All right,
okay, thank you.
Let's move on to the next stage. 3 minutes of preparation by the opponent, starting now. All right, is the opponent ready to pull up their slides?
Okay, switch
Is
slides.
it- yeah, okay, wait.
Is this center?
Oh, it's not sharing.
Okay, I'll run the clock now. Please be good.
Not up sharing. There's no option to share. Okay, when I start talking, I'll share.
Okay. So thank you again for the wonderful reports. So first, I would like to just introduce the problem statement one more time. The glass tube with a sealed top is filled with water and mounted vertically. The bottom end of the tube is immersed in a beaker of water and a short segment of the tube is heated. Investigate and explain the periodic motion of the water and any vapor bubbles observed. So overall, the tasks for this experiment were to qualitatively explain the phenomenon, which we believe was partially fulfilled, develop theory about the shape of the vapor bubbles, which we believe was partially fulfilled, and quantitatively explain any periodic motion that was observed, which we don't think was fulfilled. Experimentally, we think that the tasks were to reproduce the oscillatory phenomenon, which we believe was fulfilled, accurate heat and motion measurement method, which we believe was fulfilled, and develop a strategy to input heat into the system, which we believe was fully fulfilled. So first, a quick summary of the report. Essentially, what the reporter talked about was dynamics, heat exchange, and superheated vapor. They had a robust experimental setup and varied a significant number of parameters: heat added, width of tube, length of tube, and water temperature. So now let's go into a couple of merits and improvements. So first, some merits. The reporter very well modeled density change in the fluid, considered capillary forces in the system, and accounted for the temperature of the bubble. Some small areas for improvement are that the smaller oscillations are not thoroughly investigated, the theoretical models are not completely testable, and the effect of key parameters are not qualitatively or quantitatively explored. Next, we can go into some merit and improvements for experimental. The merits are robust experimental setup, where the reporter used a thermocouple and a variable power supply to supply a constant heat into the system, obtained motion time graphs with amplitude over time, verified superheating with a thermal camera. However, there were some areas for improvements, such as the lack of comparison between the theory and experiment. For example, we think that a longer motion time graphs and 6 periods isn't not sufficient to observe the changing frequency. And secondly, there was only qualitative comparison. We also think that better data processing was required and deviations were not thoroughly analyzed. Finally, we think that thermal equilibrium was not properly examined, and we proposed to the reporter to run the experiment for very long periods of time in order to achieve an equilibrium in the system. Going over what we're going to be going through in this discussion, our first amplitude time graphs, basically going through the different peaks that are observed, the number of periods, convection within the system, the periodic motion of the bubbles, and the actual bubble profile itself in order to further expand on what the problem statement is asking us to do. Thank you. I now invite the reporter up for a discussion. Okay, Lily, could you please share your slides?
Yeah, of course.
Okay, so the first thing that I wanted you to do is, could you please go to slide 23?
Okay. Oh, shoot. Sorry, my computer's frozen. Give me a quick sec. Sorry, oh god. 22?
23, sorry.
Oh, 23, yes.
So I just wanted to go back and could you explain a little bit more why the graphs are sort of like one is going under? If you could remove the banner, that would be great.
If I could what, sorry?
Remove the green so that we can
yeah.
Yeah. Great, thank you. Could you please explain why that lower positions they're much closer, and then at higher positions they get further apart, and additionally explain why one of the graphs is kind of crossing under the other one?
Yeah, for the crossing under, I explained earlier, as I explained how it essentially reaches its thermal equilibrium maximum. And just to redefine the geometry, 0 is the top of the tube. So it's like further you move down, like the greater the position is, it's actually moving down, which is closer to the heating source. So I think that answers both of your questions.
Okay, and how long did you run this experiment for?
I ran each one at least for 20 to 30 minutes to reach its equilibrium, depending on its
okay, and you think that this reached thermal equilibrium in all scenarios, even when you had higher power inputs?
No, I varied each power input and waited for 20 minutes, and then I record down the thermal equilibrium.
You think that even at higher power inputs, you still reach thermal equilibrium in 20 to 30 minutes?
I waited for at least when it's at stabilized. So I put on the thermocouple for max, and I see the max value doesn't change for at least 15 minutes, and then I record down my data. So in this case, I would. Okay.
Next, I want to talk to you about slide 27.
Yes.
So could you explain a little bit what is happening over here? So first of all, what are the axes? And second of all, what is this 30 degrees and 60 degrees?
Oh, I'm so sorry. The graph was not updated with the axes. But once again, this is similar to the previous one where this is the time, and this is the essentially the amplitude, and well, in centimeters, but the amplitude of the oscillation. It's still the oscillation with respect to the water level in the beaker, and the 60 degrees is referring to the water bath temperature. So the initial water bath temperature that I put into the beaker, which the tube is immersed in. So here we can conclude that basically if I start off with filling my beaker with a higher temperature of water, this allows the system to pretty much like increase its frequency in terms of oscillation, because if we think about the system, now initially has a heating and somewhat condense, but now this condensation, I don't know if you guys see my camera, but this condensation is essentially like having greater temperature, and this is allowing the system to take it in easier because with respect to our earlier mentioned temperature difference. So it takes it in, and then it's heating it up easier. So in this case, it's like having higher frequency of oscillation.
Okay. And do you think? Sorry, I don't want to interrupt you, but do you think that the temperature of the water in the beaker is going to change due to convection?
Oh, it does. It does change, and in fact that we modeled this with, as I mentioned earlier in our experimental setup, we specifically have a thermocouple that's put into the beaker to make sure that we can pretty much monitor the beaker temperature in a relatively reasonable range. So we to take our data, we add warm water in if we want to keep it in the range, or add cold water. But in general, if I just run this experiment without adding anything, the beaker water temperature will increase, and it will increase dramatically if we use high power. And sorry, what's your second question?
My second question is, could you explain why there is a slight decrease in the amplitude on your 30-degree graph?
Okay, you mean like this shift? Okay, this, as we mentioned earlier, so first, I would like to say that the noticeable difference is very minimal. And another thing is, when we mentioned earlier that there is the change in gas accumulated, so it essentially brings up to some degree of uncertainty, but ultimately, also it's tracking error. But ultimately, we just want to look at the peaks, and we did make sure that the peaks correlate with the pulsating bubbles when we're tracking it.
Okay, so I just have one question. Do you think that there's a significant trend for the peaks of your, like the highest amplitude? Because if you were to draw a line along the highest peaks, that's almost a sinusoid, right? Is there a particular reason why this might be?
I don't think it's actually sinusoidal, because if we, this is just a selected region for demonstration purposes. If we select a longer time segment, it's going to be very crowded and we're not going to see anything. But basically, if we look at the entire duration, it's not really sinusoidal. This amplitude change is really just the tracker itself, and due to the image taking in the pixels.
And this is a point I was going to bring up later, but I think you could run your take your data over longer periods of time so we could properly analyze those sorts of patterns, but that's okay. Next, I wanted to go to the previous slide. I may have misheard you, but did you say that there's no effect of amplitude, like the power input has no effect on the amplitude?
Yes, we want to say it's very minimal because theoretically it's very minimal, and experimentally, if we actually look at the change, like this little change, and if you don't mind, I can show you this one. It's very messy, but this is like adding error bars, and so it's ultimately their amplitude kind of fall into each other, and again, due to tracking errors, we can't make sure that it's like absolutely precise. But in this case, because we're only changing the power, and changing the power fundamentally changes the heat that's given in that current segment. But as we mentioned earlier, the amplitude is decided by the volume, that's the volume and ultimately the size of the Taylor bubble, which we by changing the by changing the power, it doesn't necessarily change the size. We only define changing in size, or at least significant size in the bubbles, by a change in like the segment of heated region. So that's what we mentioned by like heated segment length. So in this case, we did not vary the heated segment length. We will only vary the power input. Therefore, we don't think that this caused a significant change in the amplitude observed.
Okay, I disagree. I think there's a significant change in amplitude, but that's okay. We can move on. Next, I wanted to just ask, did you do any qualitative or quantitative examining the bubble profile? Because the problem statement said to examine the vapor bubbles. So did you do anything about their shape or their edge? Because you saw that they were unique.
Oh yes, shape. The geometry is defined here. It's like more flat on the bottom, where it's like more circular and pointy on the top. And this is just because of buoyant force and viscous drag balance, and also the condensation that we mentioned earlier. And in terms of quantitative or just experimental verification, we weren't able to track the bubble because it's literally just disappears in like 3 frames. So I couldn't really track anything. However, I think that ultimately, we know that the film thickness will not change as long as we keep it, as long as keep the condition same. It will reach its technical film thickness, which is this thickness here. And so that we know that the width, let's assume that the Taylor bubble is relatively the same. So by changing the length, it will change the volume that's displaced, which I think we could be observed using amplitude. And I would rather explain the change in bubble size with the change in amplitude, which is why in the final parameter we said that by changing the heated segment length and the width of the tube, we can change the bubble. We can ultimately change the bubble volume and change the amplitude.
Okay, right, that makes sense. Thank you. Would have appreciated a little bit more on the shape itself, but that's okay. You focused on other things. I wanted to ask, you mentioned that you did have spherical bubbles occurring, correct?
Mm-hmm.
Yes, okay, great. So I wanted to ask, do you think that the noise on your amplitude time graphs is caused by these spherical bubbles forming? Like in between your large Taylor bubbles?
I would say it is this oscillation, or the noise that we call, if we want to look at a cleaner one, this one, I would say from my observation is mainly like the oscillation of its kind of balancing after it bounces. And that little vapor bubbles is really not changing anything, because one, it's in a very short segment of time, and two, when we actually like observe it, it's like it doesn't always happen. It's more like a segmented time when you will realize like the period is kind of like it has small bubbles and dramatic increase in Taylor bubbles, and there will be a period of just repetitive this. But then ultimately, change in parameters, as we mentioned, like pressure, like temperature of the volume bath is like continuously changing. And because it's a thermodynamics experiment, it's very delicate. So with these kind of little changes, it will ultimately change the system kind of. So that's why I don't think these little bubbles actually affect anything.
Okay, great. Thank you for that fruitful discussion.
All right, let's move on to the next stage, which is the opponent summarizes the discussion for 1 minute. You can begin.
Okay, great. So thank you so much for that discussion once again. So essentially what we covered through this discussion was a clarification of the thermal equilibrium graph and the intersection. We discussed the monitoring of temperature within the system, analyzed some decreases in the amplitudes on the graph and the different errors that might cause that, such as tracking error. We discussed improvements to the experimental, such as longer tracking periods to analyze trends, as well as things like a decaying period or a sinusoidal properties. We also discussed the amplitude's dependence on power, and also looked at some further insights like the profile of the bubble, and also discussed the description of the vapor. Finally, we also discussed the noise and the different errors on the amplitude time graphs. So we discussed the possibility of this being due to spherical bubbles and also the root of this data noise. Thank you.
All right. So next step is questions from the reviewer to the reporter and opponent. Reviewer, you can
All right,
start
thank you.
now.
So to the reporter, is the frequency periodic?
The frequency, we can't say it's entirely periodic, because if we consider the laminar and
All right, thank you. To the opposition, would you agree?
I would not agree. I think that the oscillation is periodic, but
All right,
it does have a decaying frequency.
Now to both to our reporter, would you say this is an open pipe system or a closed pipe system?
This is not a closed pipe system
Okay,
because we have
to
a
the opposition,
reservoir
would you agree?
connected.
To the opposition, would you agree?
It's a not a closed pipe system now.
All right, thank you. To the reporter, did you observe temperature gradually go up with time?
Temperature of what?
Temperature of the system, of the water.
The water in the beaker or water
Yeah,
in
in
the
the
tube?
beaker.
Yes, as I mentioned earlier, we noticed like noticeably
Okay, so
increase in the
until
temperature.
did you reach thermal equilibrium? Did you observe it until it reached thermal equilibrium?
You mean the thermal equilibrium of the water
Did
from
you
the bottom?
did you track it until it reached thermal equilibrium?
You see, if we have the power, we consider the thermal equilibrium.
Is it a yes or
the
no? Yes or no? Did you reach thermal equilibrium?
Yes.
Okay, thank you. So now I'd like to ask the opposition. What would you say is the most important parameter?
I would say probably the heat input is the most important parameter, or
All
the
right, thank you.
diameter.
To the
of vertical.
reporter, which one would you say is the most important parameter?
The heat input is most important
All right, thank
parameter
you.
for the
Now,
frequency.
to the opposition, would you say the coloring of the water had an effect on the boiling point?
I don't think it has that significant of an because it was a water-based dye. I don't think it had
All right,
that
thank you.
significant.
And now to the reporter, for your experiment, did you change the wrapping of your wire?
Yes, I changed the length.
All right, thank you.
And the number
and how did you record bubble sizes?
I used tracker.
All right, and to the opposition, would you say that like these parameters had like the wrapping of the wire would have a major effect on the phenomenon?
It would have an impact on the volume of your bubble. Yes.
All right, thank you. And now to the reporter, was the experiment carried out in one location in one time frame?
By one time frame, that's impossible, but in one location, yes.
Okay, yeah. But were the experiment like what was the time frame between various like different experiments? How many days apart were they?
Oh, I did it in one night.
All in one night.
Yeah.
You didn't. Okay, all right, thank you. Yeah. So for opposition, I was wondering why you thought there would be a significant change in amplitude.
Because of the fact that when you input more heat into the system, it allows the heating to occur faster and also more. So the bubble is going to be expanded. It's going to be a larger bubble if you input more heat into the
All
system
right.
compared to when
To
you
the
input
reporter,
less.
what would you have to say in response to that?
I would say that it is true that it's more system, but because the convection is dominating the system, so I disagree that it will have major impact on the amplitude.
All right, thank you.
All right. 2 minutes of preparation of the reviewer starts now.
Okay. I'd like to start now. All right, so my name is Sterling, and I'll be representing UTS MMN on problem I, Ponyo C2. The problem statement reads as follows. And yeah, here is the video of a phenomenon. And yeah, so problem statement, a glass tube with a sealed top is filled with water and mounted vertically. The bottom of the end of the tube is immersed in a beaker of water and a short segment of the tube is heated. Investigate and explain the periodic motions of the water and any vapor bubbles observed. So tasks, one was to create a reliable and accurate experimental setup, which I think the reporter did. Qualitatively explain the phenomenon, which I also think the reporter did. Investigate key parameters. I don't think this was expressed very clearly in the reporter's slides, and not really discussed in the discussion period. Also, for another task is to predict water and bubble patterns using theoretical models. I think this was somewhat done by the reporter with her graphs. Task 5 is to demonstrate that predictions sufficiently matched observed bubbling patterns. I don't really think that this was like theoretically done. It was more experimental proofs. And then 6, analyze the impact of each identified key parameter on bubbling properties and impacts. I don't think this was mentioned in the report, and I don't think this was discussed during the opposition discussion. So yeah, summary of the report. I think some theoretical analysis involved dynamics, heat exchange, and superheated vapor. Some experimental confirmations involved oscillation of water level, dry tube heat loss, and varying power. So in terms of the reporter, I think there was a controlled experimental setup and looked through various theoretical models, and theoretical models explained why theory equations applied. Sub-experiments sub-experiments were also used to prove prove assumptions made in each model. I think that was well done. Some next steps, perhaps varying key parameters and explaining that. Direct theoretical prediction. And I would appreciate more details on the experimental setup because I don't think the wire wrapping was mentioned in your presentation until I asked, and whether you changed that was not clearly mentioned. I would also appreciate experimental to theoretical and direct comparison. So we know exactly whether your theory quantitatively describes it, and you do have a lot of equations. So I would have appreciated a combination of those to see if all those equations could actually describe the phenomenon that was observed. Also, I noticed on your experiment that the power supply sort of had slight shifts, and the data was going, the values were going up and down. So I would have appreciated perhaps a graph of that and seeing how it changed over time. And I also appreciate more graphs and error analysis because as equations are good, but understanding them graphically can also help everyone better understand the problem. The summary of opposition to some key insights include smaller oscillations were not thoroughly investigated. And there was a lot of discussion on each experimental graph, including amplitude versus voltage, thermal equilibrium, and frequency graph. I would have appreciated more on parameters. So merits, so good tasks, I think were identified for the reporter. Yeah, and then I appreciated the reanalysis of some graphs, including the time taken to reach equilibrium for a position along tube against displacement. From possible next steps, I would have appreciated more diverse range of topics, including discussing key parameters. I think a lot of time was spent on the quantitative data and on the graphs. And also maybe a more focus on qualitative understanding behind theoretical models and theoretical equations. Also more points of the discussion rather than just simply analysis of the graphs. Yeah, a point raised by the opponent was that does temperature of the water change with convection? Temperature, and the reporters mentioned that the temperature of water does change with convection. I think I would agree with the reporter because temperature of water should change as convection involves the movement of heat. Yeah, so now opponent also mentioned that the reporter should take data over longer periods of time. I would agree with the opponent because it's important to analyze some trends. Also, the amplitude, I would agree with the reporter on this amplitude and voltage graph.
So yeah, right, let's finish the presentation right now.
Yeah, thank you. Yeah.
All right, cool. Time is up, unfortunately.
All right.
So next stage, 2 minutes of concluding a remark by the reporter. Please go ahead.
Okay, first of all, I would like to thank the reporter and the opponent for the fruitful discussion. I think we had lots of insights driven for our key parameters of impact on the overall system. So today we discussed about the frequency and the dimension and the vapor bubble profile. I think those are relevant parameters to this problem, which I think the discussion were very helpful in terms of further investigation on this problem. In terms of the time segment of experiment that both the reporter and the opponent brought both the reviewer and the opponent brought up, I would say that I think my data taken is in a very reasonable period of time, because as the time increase, there are also uncertainty with the temperature increase in the water beaker. So I would say that experimental wise, I think my data are relatively useful. And in terms of personal contribution for this problem, I think I was able to create a tube that has like very precise measurement of the temperature across different position of the tube. And I think this is very helpful in terms of helping us to understand the entire process and understanding how the temperature exactly evolves over time with regards to the different sections. For example, tracking the topmost thermocouple allows me to know that the temperature of that is usually stabilized at like around 40 degrees Celsius or 30 something degrees Celsius. And because I know that, therefore, when I'm considering why the bubble accumulates, I would avoid thinking that it's because it has too high of a temperature and the water can't condense. So it helps me to clarify a lot of further insights that could potentially be helpful for further investigation on this problem. So finally, I would like to thank the reporter, the opponent, and the reviewer again for the amazing discussion. That's it for me. Thank you so much.
All right, let's move on to the next stage. Question of the jury. Anyone that wants to ask a question, please give me a hands up emoji reaction. All right, please go ahead.
Sure. So question to the reviewer, then opposer, and then reporter in that order. Please be brief. This phenomena, do you believe it can be used as a timing method, i.e. a clock? And if so, for how long? Please be brief.
No, I don't think so, because the periodic, I think it was like pseudo periodic and like quasi periodic actually. So like I don't think it would have been accurate. And like temperature would have increased with the number of power, so like that would have affected it.
Sure. And to the opposer?
I agree with the reviewer. I don't think that this could be used as a clock because of the decaying frequency of the oscillation.
Thank you. And reporter?
I agree with the above, and in addition, I think because it's thermodynamics, it constantly changes. So I don't think it will be an accurate measurement of time.
Okay, thank you.
All right, next maybe Neil. Please go ahead.
Okay, first comment. I'd like I'd like to see the reviewer in court one day. But my question is to the opposer, the opponent. Earlier in the 2-minute section in your barrage of questions, one of your questions was you asked for what is T infinity in the Grashof number. Could you elaborate on why you asked that question?
Oh, I think she just didn't define that variable. I just wanted to make sure it was temperature. Yeah.
Okay, because I mean, part of the game is to trap your reporter, and the way it was deployed is as if you threw the trap into their face or on their face, but there is a certain elegance to slowly leading them into a trap. So that was what it looked like. But anyway, thank you very much.
All right, anyone else have any questions? Yeah, Peng Hao, please go ahead. We can't hear you. Peng Hao? All right, maybe we can come back to you. Maybe we could go to Ali Reza.
Okay, so this question is for all three. If hypothetically you could have changed the viscosity of the liquid to something higher, like blood, right? Do you think you still can create the bubbles inside that high viscous liquid through this process?
I would like to say it will vary because the kinematic the dynamic viscosity ultimately brings us to a different threshold of whether we're calculating the flow itself or we're calculating the constants that we mentioned earlier, because the viscosity is ultimately a parameter that allows us to encounter whether the convection can overcome the surface and like be the main driving force that's driving the buoyant bubble and the thermal exchange. So I would say if the viscosity is very, very high, the system will eventually stop to produce this phenomenon.
What about the opposition? What do you think?
I agree with the reporter. I think that for most reasonable viscosities, it can be done if you have the right system conditions, but there will eventually be a point where the phenomenon stops reproducing. You won't be able to get that Taylor bubble formation.
Mm-hmm. What about the reporter, reviewer?
Reviewer, yeah. Yeah, I would agree with both previous parties. Yeah, and I think as viscosity increases, like the bubbles might not be able to form as large and just like slide through because it's less viscous, right? If it's less viscous, and it might go on.
Okay,
Yeah.
now let's a follow-up question. If you could have had a combination of two different liquids, let's say one liquid viscous and then something like fat or something which is highly more massive and more maybe viscous above that bubble, do you think you can push that little tiny fat by creating this bubble in some direction, let's say upward?
I think the curvature will be
Hypothetically.
hypothetically, I think the curvature will be very minimal. In this case, I suppose we're heating up the less viscous region. And because we're heating that up, I would say that a bubble will be created. However, as mentioned earlier, even with this like same viscosity system where water is like relatively less viscous, and we still see the phenomenon which the bubble just disappear halfway. So it means it doesn't have enough buoyant force to actually push like the system entirely up, especially if we would consider it's more viscous. So I don't think the capillary force and the buoyant force is after all enough to push the more viscous up.
Let's hypothetically think that you could basically warm that region not with wire, but let's say with a laser, a set of lasers shining at that region, and then you could move the laser up. Do you think the pressure is high enough to move something inside that tube?
Sorry, we're now assuming that it's still like a more viscous on top, right?
Still, yeah.
I don't. Well, if the it will really depend on viscosity difference. But let's say the viscosity difference is great, and and considering the dynamic viscosity and the capillary force, I don't think it's enough to still push it up.
Okay, thank you.
All right.
Anyone else?
Yeah.
Yeah.
We have.
I just to that question, I think it was addressed to all three. So I personally think like in terms of viscosity, I think when it's two different materials, I think density would matter more because the density or like a material on top had a higher density, right? It would be applying more pressure and it would take more force for the bubble to go up. So I think density matters more in this case.
Okay, thank you.
Yeah, I agree with what has been said so far. I think that it wouldn't work in the vast majority of scenarios. It is dependent on the difference in viscosity.
Okay.
Yeah, and just in addition, since we brought up density, I think whether the properties of the two fluids matter a lot as well. Whether they're Newtonian, non-Newtonian, miscible, or not miscible, these will all impact the eventual phenomenon that we see.
All right. So before I go to the next drawer, I just want to remind the three participants that you can only lose mark for the drawer question phase. So it's not necessarily to your advantage to say too much if you're not asked. Okay. So Peng Hao, please go ahead. Does your microphone work right now?
Yeah. Can you hear me?
Yep.
Okay, so I have a question for the reporter. So could you go back to your slides? The future insight slide.
Oh yeah. Like this one or this one?
Yeah, this one. So
okay.
There are 4 graphs on the right. So could you briefly explain them?
So here we see that with the change in capillary number, we can observe like the flow on the bubble itself. Not only that, I think this may change like the flow motion and the accumulated gas. I think this also. Oh wait, my headphones died. Can you guys still hear me? Okay, I think this still also changes the periodicity of the system. As mentioned earlier, we discussed whether it's actually like periodic or chaotic, and as our reporter, our reviewer said, it's quasi, or maybe it's a point. Can you guys still hear me? My phone. Okay. It's quasi periodic or quasi-chaotic, can't remember. But ultimately, I think the quote unquote like not that periodic is created by the turbulent force, which is in here we can see it's like when the capillary number is very low. So I think this also shows us something about how the periodicity relates to the capillary number. So that's something I wanted to add to the further insights.
Cool, thank you. So maybe we have time for one last question by Shita. Please go ahead.
Thank you, Jim. Reporter, can you still hear me? I heard that your earphones died. If you can hear me, just nod maybe quickly. No, okay. So my question is to the opponent specifically. If you remember, there was an amplitude graph where you noticed that the amplitude itself has a sinusoidal trend. My question is, if we change the mode of delivery of heat, say instead of conduction, we use something like convection or radiation, do you think that will affect the stability of the amplitudes?
I think using conduction best ensures that you're actually supplying enough heat into the system. I'm not entirely sure how you do with convection or radiation, but assuming that it was possible, those two, it doesn't really matter the method that you're supplying heat into the system as long as the heat is constant. If you have a non-constant heat that's coming into the system, that's going to definitely affect your stability. But if the heat that actually gets to the water remains the same, then the phenomenon is going to be the same. If that changes when you change your method of supplying heat to the system, then that's going to cause instability.
Okay, so the method does not matter currently, only the magnitude of heat flow does. Thank you. Reviewer, anything to add? I'm just curious.
Oh yeah, sure. So I think like I wasn't really exactly thinking about a different mode of heat transfer, but I was thinking about where the heat would be applied. Because I'm thinking with radiation, if it was like radiation in one direction, like heating radiation in one direction, only like one direction of the water molecules would get heated. So I think like in terms of the phenomenon, it also has an important like dependence on which parts of the tube is being heated, which is why I would also say like the wrapping of the wire does matter in the phenomenon.
Okay, thank you.
All right, cool. I think we're out of time for juror questions. So jurors, please send your score to Andrew as before. Make sure that your final score is an integer. All right. And then you guys can remain in this room for now. And then I will actually have a short meeting with our other committee members to sort out the finals, the award ceremony and the scores for the finals. And we will come back hopefully by 7:25, and then we will go to our award ceremony. All right. So thanks everyone for your time. Thank you to the jurors for providing the scores, and thank you for the teams for giving us such a wonderful presentation and opposition and review. All right, I'll see you guys back in the award ceremony. Hey Andrew, are you still here?
No.
Yeah. After you finish entering the score, could you join the committee voice channel? Yeah. We'll just go through the final scores and make the slides for the award ceremony. All right. Cool. I'll meet you there.
10 minutes, hopefully less.
Hey, Andrew. Sorry, give me a sec. Hey, Andrew, can you hear me?
Yeah.
How are the score entry going?
I am almost done, like halfway, or 3/4 of the way done.
Hey, Andrew, are you there?
Yeah, I have like two more.
Okay, you want to join the Discord committee voice
Okay.
channel right now? Thanks.
All right, sorry to keep everyone waiting. We are just finishing up our award ceremony preparation. Dave and Andrew and Ryan will show up very soon. So I see a lot of happy faces. You guys can see that because of my lack of sleep for the past week, I am clearly, not at my best, like mental state right now. I'll just try to do my best to say the right thing and not mess up any rankings or whatever. All right. You guys should all get a pillow. It's very helpful.
Are you gonna buy pillows for everyone at the
Oh
lab?
yeah, you really should. The
It's like
foam are bad.
necessary, and also like we sleep at the lab.
Yeah,
so
just
then it's
think
like
about the
a
memory
necessity.
So we should make CaYPT award just a pillow then?
Yeah.
Is that what you want?
If, as if, I won't continue in my sentence.
As if, okay, cool. So you guys from UTS, you are what, like kicked out of your school again?
No, kicked out. We came to visit.
They have this problem every single year.
No, they just
Yeah.
love us too
Oh,
much and
yeah.
came to visit us. It's
Right.
called friendship right here.
Friendship. At least we're here, right? So, yeah. See, like you see, I am clearly just here to buy my team a little bit of time, so to keep you guys entertained. I don't have a lot of talent, so I couldn't do a performance for you guys, unfortunately.
That's so sad. So will you consider continue our pillow negotiation?
Hello, negotiation.
Yeah. Sing a lullaby. We all need sleep.
You see.
Jim, you should juggle.
You see, our negotiation is streamed all over the world, eh? So
This song and let us stream like across the world. So that,
Oh
like,
yeah, and you
everybody
should
can
sing
hear it.
along.
So we know like
I'll sing along.
Yeah.
Okay. Who did not sleep last night? Okay. Who got stuck in the snow this morning? Okay. Who had to shove their driveway this morning? Makes sense. Makes sense. Yeah, I was calling on Dennis to help us time, but then he told me this morning, no power, no Wi-Fi, can't do anything. Very unfortunate. Well, you see, I said plus minus 5 minutes. Confidence interval is 68%. So we are still how many standard deviations we are away? Almost 2. Okay.
You can make that 5 sigma.
5 sigma? Are you a particle physicist? Demanding 5 sigma results? So where is my slide? Maybe we should have a group called Never on Time also. Always late. So Dave, how many more minutes do we need?
Like 1 sigma plus or minus like another 5.
So we have error bars on error bars.
Exactly, like the XKCD
Yes.
meme.
Yes. So fractal error bars. Yes.
Very iconic.
Mm-hmm.
Andrew's praying that it doesn't time out again.
See, with my wonderful timing, I thought we'll be early. Or at least on time for once, but you know. Okay, I'm just here to keep people entertained.
Tell us about your first IYPT experience.
Oh, first IYPT experience, yeah. So we didn't have anything back then. So Ryan went to this hobby shop called Sale Electronics. You guys can go there to buy some like fun stuff. So he bought us a bunch of very interesting things. And when we got there, we had a it was in Russia back then. So in 2016, yeah, I'm old, okay. So it was in 2016, it was in Russia, and then we had a local team leader, which was a participant. So he lives in like a city in Siberia, and then he had to take a 30-hour train to get to the city where we were competing. Okay, so he got there. We walked in the dorm, we saw him, and then he pulled out like a box. Okay, he opened the box, and then there's a transformer inside. And then he said, oh, we know you guys in Canada, you use like 110 volts, not 220. So I brought you this transformer. He plugged it in, turned it on, started smoking. We were all super concerned that there was going to be a fire. And then he's like, no worries, it's fine, it's normal. And I was like, okay. Afterwards, after a few days of competing, after like I think maybe something like the 3rd match or something, he went like, guys, I think you guys don't have enough problems. I think you're going to lose coefficient very soon next round. And then what he said was that if you guys don't want to sleep, I can stay up with you guys. We can do a problem on the spot. And then we did. And then the problem was something regarding acoustic lens or something like that. So we had to create some sort of a ring-like structure. And then when sound passes through, it will sort of diffract around the edge of these rings, and it will focus onto a point. And then we didn't have any equipment. We didn't know doing the problem at IYPT was even an option. And then our team leader, Stepan, being the magical person that he is, he pulled out his toolbox, okay? I think he had like screwdrivers, wires, wrenches. I think he even had a few glass rods and a blowtorch. I didn't know what he was about to do with the glass rods and blowtorch. I don't think he would be doing glass blowing, but he came prepared. And then we just did that problem like overnight. We made these rings, because these rings are supposed to be flat, right? We couldn't find anything that's like a good material. We went to like a hotel front desk, and then we went like, do you guys have boxes? And then they were like, yeah, we have some like cardboard boxes. So we got that. We cut them into circles, and then we assembled this lens.
No,
and then
screw him.
Oh, what happened? You guys don't like my story? But anyway, we did the problem, and then I went on stage to present. And then I think I got like a 6 because I was smiling. One of the jurors legit said like, "Oh, I liked your presentation because you're smiling." And I'm just like, okay, fine. So my opponent was someone from Macau. His name is special. His name is Brain, not Brian, Brain. Okay. So later on, when we went to Beijing in 2018, he was our team volunteer. So he took us around. It was very interesting. So I think now he went to University College London for undergrad, and I think he does like, I think he's a theorist, high energy theorist. Yes, he probably does something with people at CERN. So yeah.
You skipped a lot in between about Brain.
Yes, I did skip a lot about Brain. Yes, but is our score ready?
I'm still waiting.
What? Oh my god.
But it's okay.
So do you want to tell us about Brain, Dave?
I think I should talk to Andrew right now. I think we're almost done.
Okay, good. Wonderful.
You can unleash the tool you have called Neil. He can entertain everyone. He has way more talent than most people in the room.
Yes, I still remember when we were at Perimeter one year. I think when was that? Like 2017?
That was 2017.
Ontario Regionals, right? I was on stage presenting the little air horn. And then I think I was probably too nervous. I called Poisson ratio V, and then Neil corrected me as new. No, it's yeah. And then he's like, "Oh, it's not a V." I remember that. Right, and then my fit lines were pretty good, and then you said it was too perfect. R squared 1, right? And the best thing about that place was like the board with all the equations, but I think we messed it up. We erased it.
Oh yeah, I
Kinda
took
sad.
a picture of that. They were
Yeah.
really pretty. Someone went on there and like, I'm just gonna write equations in a very
Yeah.
aesthetic manner.
Yeah. If you guys are interested in a photo that we have that year, you can find that on the CaYPT website. See if you can find me or Neil or Clara. I was really hiding behind someone, honestly. But that was interesting. Yeah. I think that year also snowed a lot. We were brought there by the school bus, right?
Oh yes, to Waterloo.
Yeah.
And Ryan was actually thinking he might have to buy sleeping bags because we might get trapped in Waterloo.
Yeah.
Wait, I don't remember this. And I should have been in charge of this.
Remember we met at like the Don Mill station?
Yes.
In front of
Fairview Mall.
Fairview
The
Mall, right?
The mall.
Yeah.
This is the picture that I took at Perimeter.
Oh,
wait, Jim.
Yes.
Sorry. Can you come back into the committee?
Oh, okay. Something's wrong, I guess. Okay. I'll be back.
Is anyone here from the first match of the finals? Can someone explain to me what happened? Because someone was saying this is not what we wanted to present, and then you can see the mental duel between, who was it, Crystal and Archie. It's as if they were lightsaber dueling with words. Anyone here from that school? No, Schwartz children is here, so that's not them. But, oh, no one here is from UTS. Oh no, there are people here from UTS. Yeah, that first match, man, like I haven't seen a match that heated in a long time.
I think there was a match at Perimeter like that.
Yeah, there was one like that. But the one today, the first one was like boom, boom, boom.
Even the last reviewer was interesting. The one you want to see in court.
Yes, he'd make a good lawyer. Doesn't give the witness time to answer. Say, okay, next, moving on.
To be fair, he had a lot of questions, so he
I know.
budgeted quite well.
He-
It's like
he's-
he should have just said at the start, this one line, I expect 2 to 5 word answers. Let's go.
He seems very lawyerly, definitely. Oh, that was funny. The funniest story for me was there was one year I did it in person. I was judging, and then one of the teams, I forget which team it was. It was right after the opponent gives his speech, and then his last line was, and now I would like to invite the reporter to come down and discuss. Because normally the reporter is far back, but for some weird reason, the reporter was also on stage. And then he still said the line, I'd like the reporter to come down to the stage to discuss. And then the reporter is literally 1 meter to his right. And I got pissed and I said, she's right next to you. That was fun.
Are you sure it wasn't breaking down Andrew's system by clicking a wrong problem? And something to go through that
No,
shouldn't.
but that was supposed to be never told in public because
And they're causing a chain reaction.
Okay.
A literal nuke.
Okay. So, hey everyone. So I must apologize. Something went wrong with our scoring method. Okay. So you guys sent the scores to Andrew, right?
Yes.
So he left the Zoom call. So his chat was actually lost. So if you remember your scores for the 3 teams, could you just send that in the juror channel again?
I sent it to him on Discord, so that's okay. All right.
You send him to on Discord. So for everyone else that's here that judge in the finals, then if you remember what scores you gave for the last round, it's actually only for the last round. That could you please send it in the juror channel again?
Okay.
I sincerely apologize.
Okay. So yeah, Sheetal, so I'll tell the story of last year when I almost or practically crashed the system because
nuked. I'm sorry, nothing below nuclear fusion works there.
Yeah, I used a fusion bomb and destroyed the system because there were 2 teams, and because of repeated rejections and cancellations or whatever, there were only 2 problems left. Both of them were just covered immediately prior. So the other judge and I said, okay, we really do not want to listen to the same thing over and over again. And then so we talked to the teams. It's like, okay, we will pretend that we chose problem A, but you're actually going to do problem C. Is everyone okay with this delusion? And everyone in the what do you call it, in the match room agreed. And then when we come to the finals, because both teams ended up at the finals. Oh, Oscar's son, yes. Yes, I think he was in that team. Yeah, so when we show up to the finals, Jim is asking, wait, why are you doing this? I thought this was just banned. And then he looked at the record and says, oh, but you did not do this. Neil did the right thing. And then he doesn't realize that I lied on the system. And I think this was the meme from that year. Let me look for the meme from that year on CaYPT 2022. Yeah, this was copy image. Let me copy it to the chat to everyone. This was the meme that year. Like I had a choice of following the problem, but then had to present it again or tricking the entire system. And of course, I just chose the button on the left and didn't really care. And then it crashed this. Oh, amazing.
So it crashed it on, this was day 1, round 3. It crashed it on day 1, round 3.
Day 2, right before the finals.
No, it crashed it on day 2 between 4 and 5 once. And then it crashed it again between 5 and the finals.
Yes. Yeah.
I know this because the crash between 4 and 5 occurred in my room.
Oh, okay. this was another one. Like this was the other nice meme. Follow, yeah. The other judge and I, we did not want to listen to the same thing. It's like a third or fourth time listening to the same thing, but we did not know about the bands that you are supposed to follow them. I thought you could trick them, so I tricked them, and then crash the system.
I'm pretty sure every juror agrees with you when they say that we have 5 problems. Let's just listen to all of them at least once, as opposed to listening to the same 2 problems. I don't know, for 3 continuous matches on the first day.
Yes. In my first day this year, last week, so last Saturday, there was a reporter and then opponent. Opponent challenged problem A, and then the next round, the reporter challenged problem A also, and I had to tell them, you know each other's weaknesses. Like both of you are pointing guns at each other. Both of you know that the guns don't have any bullets, but you're pretending as if the other guy doesn't know the gun has no bullets, and you're just pointing it at each other anyway. So it was just so funny.
Draw, like what? Calling the double bluff.
Yeah, like calling a double bluff, despite the fact both of you know the guns have no bullets, because you know each other's questions already.
Let's calculate the fractal dimension of that bluff.
Oh yeah, and then today in my room I, we had a team that rejected 3 challenges in a row, and then I was worried. Then the system eventually prevented them from rejecting any more.
I don't think you can. So wait, you reject 2 without penalty. The third one gives you a penalty already, right?
Yeah, I told them. Yeah, and they said, "Oh, no, because 2 of their teammates were not present.
I see.
They have no choice but to reject." I mean, they could present and make stuff up on the spot, but that's gonna be hard. Earlier, when I was advising the opponent, I forget which team, the one who asked that random question in the Groshev number, like, why'd you ask T infinity? And then I thought it was a trap, but it was a very poorly executed trap, and I wanted to demonstrate, here's how you do a good trap. And then you freak your reporter out. Don't just fling the question and hope it stuns them.
That's what PhD committee meetings are all about. They trap you so well. I've been trapped. Like I've done these like 3 times now, and still I get trapped every single time.
Yes, yeah. There's a certain elegance to trapping the person you're challenging. Don't just throw the question at him. Yeah.
And once you get trapped, it's almost as though you just throw the gauntlet down and say, "Well played."
Yeah.
Don't even try to get out of it.
Oh, Oscar, are you going to undergrad next year already? I think you are, right? From Schwartz Children? You're in grade 12 or grade 11? Yeah, I think you would be in undergrad next year. And who else? Yeah.
I'm so sorry for the delay. We do have the scores. We will have that ready, and we'll start at 8:10. So sorry. I know it's a long day. I'll try to keep the award ceremony relatively brief so we can all get some much needed rest.
Hello.
Hello.
Did
So
you
we
get the
do have everything ready?
file?
Yes. Yes.
Okay,
Yes.
cool.
Yes. I'll screen share and I guess we can begin then. So Dave, could you just send a ping to everyone in the server?
Yeah, sure.
So that we're tell them that we're starting. All right, let's start. So hi everyone, welcome to the award ceremony of the 7th Canadian Young Physicists Tournament 2023. So I would like to thank STEM Fellowship, our parent organization, a student-run federal charity. We'd also like to thank U of T Physics, Waterloo Physics, McMaster Physics, and BCAPT, British, BC Association of Physics Teachers, and also NSERC for helping us spread the word to recruit our jurors. So let's present our individual awards first. So let's see. Okay, so the first award that I want to present is the Best Experiment Award. This award is nominated by the jurors of the competition, and it is in recognition of the best experimental setup and data that the jurors have observed in your selected matches. So the Best Experiment Award of CaYPT 2023 goes to Yuejin Dong from Team Schwarzchildren for her work in fractal fingers. Maybe Dave, Andrew, Ryan, we can do a yay. Congratulations. And the next individual award that I want to present is the Best Theory Award. This award is also nominated by the jurors in recognition for the best theoretical model and analysis presented in the 5 selected matches of our tournament. So we would like to present the Best Theory Award to Selena Guo from Team UTS Shroomskis for her work in Faraday waves. Woo! Congratulations. But last but not least, our final individual award is something special named after Mohammad Asadi Lari. It is the Mohammad Asadi Lari Leadership Award. So Mohammad was actually the founder of STEM Fellowship and of CaYPT, but tragically he passed away in the Ukrainian International Airlines Flights 752 disaster back in 2020. And we named our leadership award after our founder, Mohammed. So this award is nominated by the members of the CaYPT committee, and it is in recognition for leadership within your team. So I would like to invite Dave to present this award.
Yep, and so we would like to present this award to Emma from Team UTS Angry Birds for her efforts as a leader to bring her team together in the competition.
Congratulations, Emma. And next up, we will move on to our team awards. So first up is our participation awards, which I will be presenting. So participation awards, we will start off with Team Schrodinger's Kittens, who joined us in physics match number 1, but unfortunately could not continue in the competition due to health reasons. Next up is Team Schrodinger Treats, who had a total sum of points TSP of 131.6. They are from Semiahoo Secondary School in Surrey, British Columbia. Congratulations. Next up is Team Chromatic with TSP of 158.4 from St. Robert's Catholic Highs from Markham, Ontario. Congratulations, Team Chromatic. And next up is Team SMUS Schrodinger's with TSP of 162.5 from St. Michael's University School from Victoria, British Columbia. Congratulations. Next up is Team MGCI with TSP of 168.6 from Margaret Collegiate Institute in North York, Ontario. Congratulations. And the next team is UTS Navier-Stokes with TSP 169.5. They're from University of Toronto Schools from Toronto, Ontario. Congratulations. And next up is Team Schrodinger Litter, TSP of 172.0 from Semiahoo Secondary School in Surrey, British Columbia. Congratulations. And also next up is Team UTS Sigma with TSP of 173.6 from University of Toronto Schools from Ontario. Congratulations. And next up is Team Schrodinger's Alive Cat Girls with TSP of 178.0. They're from Oakville Trafalgar High School in Oakville, Ontario. Congratulations. And next up, we will move on to bronze medals, in which I will invite Andrew to present.
Okay. So first up, we have Team Woods 23 with a TSP of 183.6 from the Woodlands Secondary School from Mississauga.
Congratulations.
Next, we have Team Non-Affiliated, TSP of 183.7 from Independent School from Toronto. Congratulations.
Congratulations.
Next, we have Team UTS Angry Birds with a TSP of 190.2 from UTS in Toronto. Congratulations.
Congratulations.
Next, we have Team UTS Anti-Entropy with a TSP of 193.7 from UTS in Toronto.
Congratulations. Next up, I would like to invite Dave to present our silver medals.
All right, so the first silver medal goes to Team Schrodinger's Dead Cat Girls with a TSP of 196.0 from Oakville Trafalgar High School from Oakville, Ontario. Congrats.
Congratulations.
The next silver medal goes to Team STR Lagrangians with a TSP of 199.9 from a hybrid school in North York, Ontario. And the next silver medal with a
Congratulations.
With a score of 42.3 in the final round goes to
Drum roll, please. Goes to
Team UTS Shroomskis from UTS in Toronto with a final score of 42.3.
Congratulations. And next up, I would like to invite Ryan up to present our gold medals to the top two teams in the final physics match of today.
All right. So for the gold medals, the first gold medal award goes to with a final 47 UTS Mort's Mistress. Okay, from UTS, University of Toronto School from Toronto, Ontario. Congratulations.
Congratulations.
Congratulations. All right. So the last one, okay, which is the final team that go with scores the final with 50.1. That's Team Swartz Children with a hybrid team from North York, Toronto, Ontario. Congratulations.
Congratulations.
Thank you. Great job, everybody. Great job. Okay.
Great job, everyone. Yeah. So I'll finish with a quick concluding remarks then. So thank you everyone for joining us through this, I guess, like more than 1 week long of competition. I know that during these few days, you guys have been working very hard on your problems, your experiment, your theory, and also your presentations. Many of you guys staying up like multiple nights. So I would like to congratulate all of the teams on your achievements, and hopefully you guys have learned a whole lot from this competition, not only the physics, right, but also in general, how you would tackle a hard problem, how to do research in science in general. So great job to all the students. And next, I would like to thank all of our jurors, right? This competition will not be possible without your work. And I would like to thank all of the organizations that has spread the message for us in order to allow us to recruit all of our jurors. We had 45 jurors, which is a record-breaking number of jurors. So I would like to thank again STEM Fellowship, our parent organization, for helping us with the administration, and also the U of T Physics Department, in particular, Supreet, which is their special projects manager for helping to reach out to other schools to help us recruit jurors not only at U of T, but also at other institutions. I would also like to thank the physics department of University of Waterloo and also McMaster University for forwarding our email regarding juror recruitment to all of the jurors so that we can recruit such a hardworking and diligent and responsible group of both grad students and teachers to judge in our competition. And finally, I would like to thank the BC Association of Physics Teachers for inviting me to do a talk in one of their meetings and helping us forward our email to their members so that we had quite a few physics teachers from the education background and from the field of education to be part of our jury team as well, to make our jury team very diverse in terms of age, experience, and so on, right? And finally, I would like to thank all of our committee members. So first up, I would like to thank all of our student committee members, in which a few of them are participants themselves. They've been working on a lot of our committee work related to things like student resources and references, and also video editing and stuff like that. So their volunteering allows us to provide all of our students with the resources they need to start off with their research. And then I would like to thank our other committee members who are not like students that are currently competing. They're in undergrad. They have generously volunteered their time to help us make this competition possible. And I would like to thank especially our information team for testing our system again and again to make sure that our system is actually working and behaves as we expect during the competition. And as we grow to the size of 18 teams, it's impossible to keep track of all the scores and bands manually. So this will not be possible without our current information team members, Jerry, Darren, and our information team lead, Leo, for organizing this year's maintenance and testing of our website and of our system. And finally, I would like to thank two of my associate directors of the committee for their work. So Dave, you judged in the competition, and Andrew, you helped out with timing. And Andrew is the original person that set up our system to allow us to essentially be able to grow the competition to the size that it is today. And finally, I would like to thank Ryan for training all of the jurors early in the morning and helping us with all of the logistics regarding Zoom accounts and also potentially in the future juror honorariums. And I would like to also congratulate Ryan on being elected EC of CaYPT. So Ryan will be responsible for picking some of the problems that you guys might see next year. And yeah, speaking of problems, I'll also thank the teachers that participated in the problem selection committee this year as well. Many of them couldn't be here because of other commitment, but I would like to thank them for their work. So hope everyone enjoyed the competition, and I guess we'll close the competition here, and I might see you guys maybe in the next year then. Maybe some of you guys in camp as well. And
just to close it off, another time, I would like to thank Jim for your effort. All right, so thank you very much. You took over this, and then you put a lot of your effort every year. Great job. Okay, great job. Thank you very much. So I'll pass it back to you, and then hopefully everybody can go home. Okay, thank you.
All right, thank you, Ryan. Thanks, everyone. Have a good night's sleep. Enjoy your weekend and potentially March break next week.